Welcome to R Data Mining Projects by Pradipta Mishra, a video course by Pact Publishing. I'm Mark Thomas and I'll be Pradipta's voice for this course. Pradipta Mishra is a data scientist, predictive modelling expert, deep learning and machine learning practitioner, and an econometrician. He's currently leading the data science and machine learning practice for Marfoy Analytics, Bangalore, India. He holds a patent for enhancing planogram design for the retail industry. Pradipta has published and presented research papers at IIM Ahmedabad, India. He is a visiting faculty at various leading B schools and regularly gives talks on data science and machine learning. Pradipta has spent more than 10 years in his domain and has solved various projects relating to classification, regression, pattern recognition, time series forecasting, and unstructured data analysis using text mining procedures, spanning across domains such as healthcare, insurance, retail, and e-commerce, manufacturing, and so on. In case you have any queries, you can contact him on Twitter via @mishra1_pk. The R language is a powerful open-source functional programming language. At its core, R is a statistical programming language that provides impressive tools for data mining and analysis. It enables you to create high-level graphics and offers an interface to other languages. This video course explores data mining techniques and shows you how to apply different mining concepts to various statistical and data applications in a wide range of fields. We'll teach you about R and its application to data mining, and give you relevant and useful information you can use to develop and improve your applications. This fast-paced video tutorial will help you solve predictive modelling problems using the most popular data mining algorithms through simple practical cases. We'll start with learning of programming basics using R, reading and writing data programming notations, and syntax understanding with the help of a real-world case study. It also includes R scripts for practice to get hands-on experience of the concepts, terminologies, and underlying reasons for performing certain tasks. The next section helps you to understand exploratory data analysis. It's important to get an understanding of the dataset, type of variables considered for analysis, the association between various variables, and so on. In Section 3, we'll cover the basics of data visualization, along with how to create advanced data visualization using existing libraries in the R programming language. The next section will help you understand the basics of predictive analytics using regression methods, including various linear and non-linear regression methods using R programming. You'll be able to understand the theoretical background as well as get practical hands-on experience on all regression methods using R. Finally, Section 5 shows the second method of product recommendation, popularly known as market basket analysis, and also as association rules. This is about associating items purchased at transaction level, finding out the sub-segments of users having similar products, and hence recommending the products. At the end of the course, you'll learn to use R programming to apply statistical models on data and create predictive models that are applied for performing classification, prediction, and recommendation. You'll also learn the various data visualization libraries available in R for representing data. You'll require RStudio version 3.3.1, a computer with more than 2 GB of RAM. This course is for data analysts from beginner to intermediate level who need a step-by-step helping hand in developing complex data mining projects are the ideal audience for this video course. They should have prior knowledge of basic statistics and a little bit of programming language experience in any tool or platform. So, let's begin this wonderful journey together, and I hope to see you there. Hello viewers, welcome to the very first section of the course, Data Manipulation using inbuilt R data. In this section you'll learn about various data types used in R, including vector and its operations. You'll also learn indexing, sorting and merging of data frames. Apart from this, you'll learn string manipulation and date object formatting, handling missing values and NAs, and missing value imputation techniques, flow control, looping constructs, and the use of apply functions. Now we move on to the first video of this section, what is data mining? In this video you'll learn what is data mining, its functions, the process of data mining and its relation with data science, analytics and statistical modelling. Let's begin. So, what is data mining? Data mining can be defined as the process of deciphering meaningful insights from existing databases and analysing results for consumption by business users. Analysing data from various sources and summarising it into meaningful information and insights is that part of statistical knowledge discovery that helps not only business users, but also multiple communities such as statistical analysts, consultants and data scientists. Most of the time, the knowledge discovery process from databases is unexpected, and the results can be interpreted in many ways. The growing number of devices, tablets, smartphones, computers, sensors, and various other digital devices helps in generating and collecting data at a much faster rate than ever before. With the ability of modern-day computers, the increased data can be pre-processed and modelled to answer various questions related to any business decision-making process. Data mining can also be defined as a knowledge-intensive search across discrete databases and information repositories using statistical methodologies, machine learning techniques, visualization, and pattern recognition technologies. The growth of structured and unstructured data, such as the existence of barcodes in all products in a retail store, attachments of RFID-based tags on all assets in a manufacturing plant, Twitter feeds, Facebook posts, integrated sensors across a city to monitor the changing weather conditions, video analysis, video recommendation based on viewership statistics, and so on, creates a conducive ecosystem for various tools, technologies, and methodologies to splurge. Data mining techniques applied to the variety of data discussed previously not only provide meaningful information about the data structure, but also recommend possible future actions to be taken by businesses. The process of data mining involves various steps. The first step is to extract the required data from databases and data warehouses. Next, we have to perform a sanity check on the data to remove redundant characters and irrelevant information. But at times, it's important to combine information from various other disjoint databases. Hence, look for common attributes to combine databases. Then, apply data transformation techniques. Sometimes it's required to include a few attributes and features in a model. The pattern recognition among the input features, where any of the pattern recognition models can be applied. Finally, the knowledge representation. This includes representation of knowledge mined from databases in visual form to various business stakeholders. Having discussed the process flow of data mining and the core components, it's also important to look at a few challenges that one may encounter in data mining, such as computational efficiency, unstructured databases and their confluence with structured databases, high-dimensional data visualization, and so on. These issues can be resolved using innovative approaches. In this course, we're going to touch upon a few solutions while performing practical activities on our projects. Let's now discuss how is data mining related to data science, analytics, and statistical modeling. Data science is a broader topic under which the data mining concept resides. Going by the aforementioned definition of data mining, it's a process of identifying patterns hidden in data and some interesting correlations that can provide useful insights. Data mining is a subset in data science projects and involves techniques such as pattern recognition, feature selection, clustering, supervised classification, and so on. Analytics and statistical modeling involve a wide range of predictive models, classification-based models to be applied on datasets to solve real-world business problems. There is a clear overlap between the three terminologies: data science, analytics, statistical modeling, and data mining. The three terminologies should not be looked at in isolation. Depending on the project requirements and the kind of business problem, the overlap position might change, but at a broad level, all the concepts are well associated. The process of data mining also includes statistical and machine learning-based methods to extract data and automate rules, and also represent data using good visualizations. Nice! In this video, you learned about the data mining. In the next video, you'll be introduced to R programming language. Hello! Welcome again to the next video of this section, Introduction to the R programming language. In this video, we're going to start with basic programming using R for data management and data manipulation. We'll first download R and then install it. We're going to start with basic programming using R for data management and data manipulation. R can be downloaded from this link. Based on the operating system, anyone can download and install the R binary files on their systems. The R programming language, which is an extension of the S language, is a statistical computing platform. It provides advanced predictive modeling capability, machine learning algorithms, implementation capability, and better graphical visualization. R has various other plugins such as R.NET, R Java, Spark R, and R Hadoop, which increases the usability of R in big data scenarios. The user can integrate R scripts with other programming platforms. Detailed information about R can be accessed from this link. This is the R Studio installed in my system. Let's get started with R. The opening message when starting R would be as shown in the screen. Everything entered in the R console is an object. Many objects created in an active R session have different attributes associated with them. and one common attribute associated with an object is called its class. There are two popular approaches to object-oriented programming in R, which are S3 classes and S4 classes. The basic difference between the S3 and S4 approaches is that the former is a more flexible approach. However, the latter is a more structured approach to object-oriented programming. Both S3 and S4 approaches recognize any symbol, character and number as an object in R sessions, and provide functionality where the object can be used for further computations. Next, we'll look at data types, vectors, arrays, and matrices in R. Let's create a file. There are two broad sets of data types: atomic vectors and compound vectors. There are basically 5 data types in R programming under the atomic vector category: numeric or numbers, characters or strings, factors, logical, and complex. And there are 4 compound data types: data frame, lists, array, and matrix. The primary data object in R is a vector. Even when we assign a single-digit number to any alphabet, it is a single element vector in R. All data objects contain a mode and a length. The mode determines the kind of data stored in the object, and the length determines the number of elements contained in that object. The function in R implies concatenating of various elements in a vector. Let's take a look at various examples showing different data types in R. Let's define vector x1 in a numeric format, and the number of elements is 5. See the data type of x1. You can see the data type is numerics. Same is done with mode function. As you can see, both class function and mode function return the same results, hence both determine the type of vector. Let's define another vector. The x2 vector is a logical vector having 5 elements. We'll now define its class and mode. The class and mode are both logical again. Both class function and mode function return the same results, hence both determine the type of vector. The logical vector x2, elements or values, can be written as either t or f, or true or false. Object x3 represents a character vector length of 25. All elements of the vector can be mentioned within double quotes or single quote. The factor is another form of data where various categories listed in the vector are known as levels. As you can see, vector A is a character vector with 2 levels or categories. Let's create a vector named domain with levels of categories, which are repeated with some frequency. The as.factor command is used to convert a character vector into a factor data type. Let's use it and run the command. After applying that, it indicates that there are 5 levels such as analytics, data mining, machine learning, projects, and statistics. The table command indicates the frequency table computed from the factor variable. You can see the output of. Let's create data frame called x. Let's see the class of the data frame and print the x. Data frames are another popular form of data type in the R programming language that include all different data types. A data frame is a list that contains multiple vectors of the same length and different types of data. If you simply import a dataset from a spreadsheet, the data type by default becomes data frame. Later on, the data type for individual variables can be changed. So, data frame can be defined as a matrix that contains columns of different data types. In the script, the data frame X contains 3 different data types: numeric, logical, and character. Most real-world datasets contain different data types. For example, in a retail store, information about customers is stored in a database. This includes customer ID, purchase date, amount purchased, whether part of any loyalty program or not, and so on. One important point about vectors: all elements of a vector should be of the same type. If not, R will forcibly convert that by coercion. For example, in a numeric vector, if one element contains a character value, the vector type will change from numeric to character. Let's see examples of coercion. X is data frame with x1, x2, x3 vectors. Let's define vector x1 and check its class. Create another vector x1 and check its class. You can see that one is numeric and the other is character, so it automatically converts numeric vector into character using coercion. R is case sensitive, so cat is different from cat, so be careful while assigning object names to the vectors. To know what all objects are active in the current R session, the ls function command can be used. The list command will print all the active objects in the current session. Let's take a look at what a list is, how to retrieve the elements of a list, and how the list function can be used. Next, we'll look at list management, factors, and sequences. A list is an ordered collection of objects that can contain arbitrary objects. Elements of a list can be accessed using the double square bracket. Those collections of objects are not necessarily of the same type, they can be of different types. Let's create a list. In the list, the customer ID and mobile number are of numeric data type. However, the customer name and email ID are of character data type. There are basically 4 elements in the list. To extract elements from a list, we use double square brackets. And if we need to extract only a sublist from the list, we can use single square bracket. You can see only John R is printed with double square brackets. When single square bracket is used, customer name and John R are printed. The next thing related to lists is how to combine more than one list. Lists can be combined using the cbind function, that is column bind function. Let's create again. You can see a list is created. Now create second list, mylist2. Let's combine both the lists. And then print the mylist. In the output, you can see the list of mylist1 and mylist2. Factors can be defined as various levels occurring in a categorical or nominal variable with a certain frequency. In other words, levels that are repetitive in a category variable are known as factors. As seen earlier, a character vector, domains, contains many levels. Using the factor command, the frequency for each level can be estimated. Sequences are a repeated number of iterations, either numerical values or categorical or nominal values that can be part of a dataset. Numeric sequences can be created using a colon operator. To generate sequences using factor variables, the GL function can be used. This is a very useful function while computing quantiles and graphical functions. Also, there are various other possible scenarios where you can use the function. Let's create a sequence. You can see that length of 4 between 1 to 5. Let's create another sequence. You can see the length is 10 from -2 to 0.2. Let's create a repeat function, that is, rep function. The 15 is repeated 10 times. Let's use the GL function, and this is the code for GL function. Here you can see that there are 2 levels, and don't buy and buy repeated 5 times, and levels are specified as buy and don't buy. The first line of code generates the sequence in ascending order. The second line creates a reverse sequence. And the last line creates a sequence for the factor data type. Next is import and export of data types. If the Windows directory path is set to import a file into the R system, it's not required to write the complete path where the file resides. If the Windows directory path is set to some other location in your system and still you want to access the file, then the complete path needs to be given to read the file. So check your directory using getWD function. You can set your directory by using the setWD function. Any file in the Documents folder can be read without mentioning the detail path. Hence, it's always suggested to change the Windows directory to the folder where the file resides. There are different file formats. Among them, CSV or text format is the best for the R programming platform. However, we can import from other file formats. Let's import CSV files, and this is the code required for it. I've mentioned the detailed path. Let's see column names of DT. If you are using the read.csv command, there is no need to write the header, true, and separate it as a column. But if you're using the read.table command, it's mandatory to use. Let's use read.table function with separator with equal to t and separator as comma. Let's run this code and see the names of data files and see the same output. While mentioning paths to extract files, you can use either / or double backslash. Both ways will work. In real-life projects, typically the data is stored in Excel format. How to read the data from Excel format is a challenge. It's not always convenient to store data in CSV format and then import. Let's see how to import Excel files in R. 2 additional libraries are required to import an RDBMS file such as Excel. Those libraries are mentioned, so let's import them. The code is library open bracket xlsx close bracket. You can see the output. Let's import the xlsx jar library. The code is shown. Once we are done, we can read it using read.xlsx command. You have to specify sheet name and sheet index. After specifying them, I am running them. Print the data inside the DAT file using the head command. You can see the output here. Legacy enterprise-based software systems generate data in either SPSS format or SAS format. The syntax for importing from SPSS and SAS files needs additional packages or libraries. To import SPSS files, the HMISC package is used. And to import SAS files, the SAS7BDAT library is used. So let's import the HMISC library, and this is the code for it. We're using the spss.get function to read wage.sav file. Let's use the head command to get data of SAV file. You can see the output from the wage.sav file. Similarly, import for SAS7BDAT library. You'll need to install a package, so let's go to Tools and Install Package. Let's read a file of this type, and the code is as shown. We're using read.sas7bdat function to read the file in full path. It's done, so we'll use the head command again. You can see the output of SAS7bdat file. Exporting a dataset from R to any external location can be done by changing the read command to the write command and changing the directory path where you want to store the file. In this video, you learned basic R programming. In the next video, you'll learn data type conversion. Hey, we're back with the next video of this section, data type conversion. In this video, we're going to convert various data types into another format. There are various types of data, such as numeric, factor, character, logical, and so on. Changing one data type to another if the formatting is not done properly is not difficult at all using R. Before changing the variable type, it's essential to look at the data type it currently is. To do that, use these functions. Let's check if data type of x1 is numeric or not. It's true. And data type of x3 is character or not. It returns true. Similarly, check that data type x1 is of type vector and output is true, and check if x is matrix or not. And output is false. And check if x is data frame and output is true. When we are checking a numeric variable as numeric or not, the resultant output will display true or false. The same holds for other data types as well. If any data type is not right, that can be changed using as.dot function. If you want to change as numeric, then use as.numeric function. As you can see, it's done similarly. You can change to vector using .vector function. For conversion into matrix, use .matrix function. You can see matrix form as X. For conversion into data frame, use .data.frame function. Using as.character function, even logical vector is changed from logical to character vector. But in numeric variable, nothing is changed since everything was in numeric form. Using as.factor function. When using as.character function, even a logical vector is changed from logical to character vector. For a numeric variable, nothing is changed as the x1 variable was already in numeric form. A logical vector can also be changed from logical to factor using this command. In this video, you learned how to convert data types. In the next video, we'll learn sorting, merging, indexing, and subsetting data frames. Hello, welcome to the next video. Sorting, merging, indexing, and subsetting data frames. In the previous video, you learned how to convert data types. In this video, we're going to use functions for sorting, merging, indexing, and subsetting the data frames. Sorting and merging are two important concepts in data management. The object can be a single vector, or it can be a data frame or matrix. To sort a vector in R, the sort command is used. A decreasing order option can be used to change the order to ascending or descending. For a data frame such as artpiece.csv, the order command is used to sort the data, where ascending or descending order can be set for multiple variables. Descending order can be executed by putting a negative sign in front of a variable name. Let's use the dataset to explain the concept of sorting in R as shown in the script. First, import the data. In the ArtPiece dataset, there are 16 variables, 10 numeric variables and 6 categorical variables. Using the names command, all the names of the variables in the dataset can be printed. The attached function helps in keeping all the variable names in the current session of R, so that every time a user will not have to type the dataset name before the variable name in the code. Let's now use the sort function. By default, the sorting is done by ascending order. To sort the vector based on descending order, it's required to put a negative sign before the name of the variable. The critic.ratings variable can also be sorted based on descending order, as shown on your screen. To sort in descending order, increasing is true, it can be set with the command. Instead of sorting a single numerical vector, most of the times it's required to sort a dataset based on some input variables or attributes present in the data frame. Sorting a single variable is quite different from sorting a data frame. Using this code, the data frame can be sorted using the order function. The code shows critic ratings and acquisition costs sorted in ascending order. Once it's done, let's print the I2 data using the head command. The order command is used instead of the sort command. The head command prints the first 6 observations by default from the sorted dataset. The number 1:5 in the second argument after the order command implies that we want to print the first 6 observations, and 5 variables from the ArtPiece dataset. If it's required to print 10 observations from the beginning, this code can be executed. The dataset does not have any missing values. However, the existence of NA or missing values cannot be ruled out from any practical dataset. Hence, the presence of NA or missing values, sorting a data frame can be tricky. So by including some arbitrary NA values in the dataset, the order command produced this result. The na.last command is used to separate the missing values and NAs from the dataset. They can be either placed at the bottom of the dataset using na.last is true, or at the beginning of the dataset as na.last is false. By keeping NAs separate from the order function, data sanity can be maintained. The merge function helps in combining 2 data frames. To combine 2 data frames, at least one column name should be identical. The 2 data frames can also be joined by using a function called column bind. To display the difference between the column bind and merge functions, we've taken the audit.csv dataset. You need to import the file, or you can use read.csv function. Let's create the dataset. There are 2 small datasets, A and B, prepared out of the audit dataset. A dataset will contain column 1, 2, 3, 5.7 and 9. B dataset will contain column 1, 3, 4, 5, 6. We'll now print names. Two columns, ID and employment, are common in both datasets A and B, which can be used as a primary key for merging two data frames. Using the merge command, the common columns are taken once in the result dataset from the merge function. The merged data frame contains all the rows of complete entries in both the data frames. This is the code for merging dataset from A and B in the third column. The output is on your screen. The merge function allows 4 different ways of combining data: natural join, full outer join, left outer join, and right outer join. Apart from these joins, two data frames can also be merged using any specific column or multiple columns. Natural join helps to keep only rows that match from the data frames, which can be specified by the all equals F argument. This is the code for it, and the output can be seen. The full outer join allows us to keep all rows from both data frames, and this can be specified by the all equals T command. This performs the complete merge and fills the columns with NA values where there is no matching data in both the data frames. The default setting of the merge function drops all unmatched cases from both the data frames. To keep all the cases in the new data frame, we need to specify all is equal to T. Left outer join allows us to include all the rows of data frame 1, A, and only those from data frame 2, B, that match. To perform this, we need to specify all.x equals T. Right outer join allows us to include all the rows of data frame B and only those from A that match. Specify all.y equals T. In data frames A and B, two columns are common. They are ID and employment. Using the merge command, if we select by one common variable, the other common variable would appear on the result data frame. If we select multiple data frames as a criteria to merge, use this code. Then all duplicate columns from the resulting data frame will disappear. The merge function works when two data frames contain at least one common column. If both data frames contain disjointed columns or there is no common column between the two data frames, then to combine both data frames, the column bind function can be used. Let's create two data frames. We're creating a data frame. Let's print names. A dataset contains 3 columns. They are age, income, and deductions. Similarly, create B dataset, which will contain and after printing. We will get education, marital, and occupation. There is no match between two datasets, so we'll combine them using cbind function. The column bind function prints all the columns in data frame A and data frame B and puts them side by side. Next, we'll learn indexing or subsetting data frames. While working on a client dataset with a large number of observations, it's required to subset the data based on some selection criteria, and with or without replacement-based sampling. Indexing is the process of extracting the subset of data from the data frame based on some logical conditions. The subset function helps in extracting elements from the data frame, like indexing. Let's create a new dataset using the audit dataset, and this is the code for it. Select those observations from the audit dataset where the gender is female and the age is more than 65 years. Which command is used to select that subset of data audit based on the preceding 2 criteria? There are 10 observations satisfying the condition. The row numbers of the data frame are printed. A similar result can be obtained by using the subset function as well. Instead of the which function, the subset function should be used, as the latter is more efficient in passing multiple conditions. Let's take a look at the way the subset function is used. Similar results can be obtained using subset function. The additional argument in the subset function makes the function more efficient as it provides the additional benefit of selecting specific columns from the data frame where the logical condition is satisfied. Great! In this video you learn to sort, merge, index and subset the data frames. In the next video you'll learn about date and time formatting. Hey there, welcome to the next video of this section, date and time formatting. In the previous video you learned about sorting, merging, indexing and subsetting of data frames. In this video we're going to take a look at date and time formatting. The date function returns a date class that represents the number of days since January 1st, 1970. The as.numeric function can be used to create a numeric value with the number of days since 1/1/1970. The return value of isDate is a date class object. Let's see the system time using this function. And this is the code to change the system time to date. Let's print the class of dt. The system time function captures the date and time with the time zone. When we convert the system time using the as.date function and stored as a new object in R, we find that the class of the object is date. The weekdays function returns the name of the day, such as Monday or Wednesday. The months function returns the name of the month from the date variable. Let's first look at the weekdays function. The output that I have obtained is Tuesday. And now look at the month function. When we run it, we get the output as January. Let's see the quarter function. The quarters function returns the name of the quarter for the date object. The output is Q1 since the month is January. And the year value can also be extracted using the substr command. And we get the current year as output. If the date variable given in the dataset is not in the proper format for further computations, it can be formatted using the format function. The code is shown on your screen. Using the format function you can change the format. These are the various options that can be passed to the format argument based on the user requirement. %d means day as a number from 0 to 31, 01 to 31. %a means abbreviated weekday as mon. %A means unabbreviated weekday, Monday. %m, month, 00 to 12. %b, abbreviated month. %B, unabbreviated month, January. %y, 2-digit year, 13. %Y, 4-digit year, 2013. Practical datasets contain date fields such as the transaction date in retail, visit date in healthcare, and processing date in BFSI. And any time series data contains at least one time element. To include the date variable in any statistical model, data transformation is required, such as calculating the vintage of a customer in a retail scenario. The data transformation can be done using the aforementioned options. Great! In this video you learned date and time formatting. In the next video you'll learn how to create new functions. Hi! Welcome to the next video of this section, types of functions. In the previous video you learned date and time formatting. In this video we're going to take a look at various user-defined and built-in functions. There are two different types of functions in R, user-defined functions and built-in functions. A user-defined function provides customization and flexibility to users to write their functions to perform computations. It has a general notation as shown. This is the general notation of function, where new func is function name and function is keyword and x is parameter. This is the line of code which we will include in the function. Let's create a function that will print 1 to 20. Let's create another function called myFunction, and it will calculate the square of each integer. Next, we'll look at built-in functions. Various built-in functions, such as mean, median, standard deviation, and so on, provide the user the ability to compute basic statistics using R. There are many built-in functions. They are abs x to calculate the absolute value, sqrt x to calculate square root, ceiling x to round up the number, floor x to round down the number, trunc x to truncate the number, for example trunc 5.99 is 5, round x digits equals n to round up a number. For example, round 3.475, digits equals 2 is 3.48. Signif x, digits equals n. Function rounds the number by 2 decimal points. Example, signif 3.475, digits equals 2 is 3.5. Cos x, sin x, tan x, also acos x, cos hx, acos hx, and so on, etc. gives us trigonometric values of the number. Log x calculates natural logarithm of a number. Log 10x calculates common logarithm. Exp x calculates exponential. In this video, we've learned about various functions. In the next video, we'll learn about loop concepts. Hello, welcome to the next video of this section, loop concepts. In the previous video, you learned to create functions. In this video, we're going to take a look at loop concepts like for loop, repeat loop, and while condition. We'll be learning about for loop, repeat loop, and while loop. Let's begin with for loop. The for loop is the most popular looping construct in R. Using a for loop, a similar task can be repeated many times iteratively. Let's look at a sample example of where the for loop concept is applied. In the following code, a series of numbers from 100 to 200 is created. If the null vector y is acting like a storage unit. If the condition mentioned in the code is not met, the loop is never executed. We can see that the numbers are printed, which means the conditions are met. We'll take a look at a repeat loop. The repeat loop is used to iterate a certain calculation over a vector or data frame. There is no provision to check the condition to exit the loop. Generally, a break statement is used to exit the loop. If you fail to provide any break condition within the repeat loop, you'll end up running the repeat loop indefinitely. Let's take a look at the code showing how to write a repeat loop. The break condition used in the code is if x is greater than 2.6, then it will not be executed further. As you can see, the output. At value 100, the condition is met. Next is while loop. The structure of the while loop in R is simple. It starts with a desired result that the user wants to see from the experiment. As the condition is entered in the beginning, the body of the loop will start iteration and go on as long as the condition is being met. The skeleton structure of a while loop consists of a constraint condition to start with. Here is an example. As you can see in the output, only 10, 20, 30, 40 and 50 are printed due to the condition. If we compare different types of loops in the R programming language, the for and while loop are very frequently used. Repeat loop is not used that frequently because of the time it takes to complete the run. If we compare the loops with the apply group of functions, the latter set of functions is quite effective in handling different tasks in R. Great! In this video you've learned about the frequently used looping concepts. In the next video you'll learn to use the apply function. Hi! Hey, we're back with the next video of this section, apply concepts. In the previous video you learned loop concepts. In this video we're going to take a look at various uses of apply function. We'll first use iris dataset, then lapply function is used, and finally sapply function is used. The apply function uses an array, a matrix, or a data frame as an input and returns the result in an array format. The calculation or operation is defined by the user's custom function, or using any built-in functions. The margin argument is used to specify which margin we want to apply to the function and which margin we wish to keep. If the array we are using is a matrix, then we can specify the margin to be either 1, apply the function to the rows, or 2, apply the function to the columns. The function can be any function, such as mean, median, standard deviation, variance, and so on that is built in or user-defined. Here we're going to use the iris dataset to perform the task. We're using the artpiece dataset and taking all rows and columns from 2 to 3, and then you can see the output. Let's change the value to 1 and apply to rows. It will print all the results in the rows. The lapply function is useful when dealing with data frames. In R, the data frame is considered a list, and the variables in the data frame are the elements of the list. We can, therefore, apply a function to all the variables in a data frame using the lapply function. You can see the output on your screen. The sapply function applies to elements in a list and returns the results in a vector, matrix, or list. When the argument is simplify is equal to f, then the sapply function returns the results in a list, just like the lapply function. However, when the argument is simplify is equal to t, which is the default argument, the sapply function returns the results in a simplified form if at all possible. The code is as shown, and the result is on your screen. By default, the argument of simplify is t. You can also use simplify to equal f to print the result as a list, which will be similar to lapply. When we want to apply a function to subsets of a vector, and the subsets are defined by some other vector, usually a factor, the output from tapply is a matrix or array, where an element in the matrix or array is the value of fat A, grouping G of the vector, and G gets pushed to the row or column names. This is the line of code. We get an error as acq.cost not found. You can use this command instead of this in case this error crops up. You see the output on your screen. There are other functions in the apply family of functions, such as eapply, applies a function over values in an environment. mapply, apply a function to multiple list or vector arguments. rapply, recursively apply a function to a list. In this video, you've learned about the apply function concepts. In the next video, you'll learn about string manipulation. Hey there, welcome. You're now watching the second to last video of the section, string manipulation. In the previous video, you learned lapply function concepts. In this video, we're going to take string manipulation. Here, we'll standardize the text, then use the substr function, and then pass the 4 important arguments. String manipulation or character manipulation is an important aspect of any data management system. In a typical real-world dataset, names of customers, for example, are written in different ways, such as J.H. Smith, John H. Smith, John H. Smith, and so on. Upon verifying, it's observed that all 3 names belong to the same person. In typical data management, it's important to standardize the text columns or variables in a dataset because R is case-sensitive, and it reads any discrepancy as a new data point. There can be many other variables, such as the name, model of a vehicle, product description, and so on. Let's take a look at how the text can be standardized using some functions. Let's create variable x, which contains a string. Let's run this and check its class, which is a character. Let's select substr from 1 to 12. It selects data mining. The object x in the script is a string or character object. The substr command is used to pull a substring from the string with the position defined in the function. If certain patterns or texts need to be altered or changed, then the sub command can be used. There are 4 important arguments that the user needs to pass: the string in which a pattern needs to be searched, the pattern, the modified pattern that needs to be replaced, and whether case sensitivity is acceptable or not. The strSplit function helps in expanding the letters from a string. The subcommand is used to alter a pattern that is not right in the string. The ignore.case option provides the user a chance to keep the case sensitivity on or off while searching for the pattern in the defined string. Cool! In this video, you learned about string manipulation. In the next video, you'll learn about NA and missing value management and imputation techniques. Hello! We're back with the final video of this section, NA and missing value management and imputation techniques. In the previous video, we saw string manipulation. In this video, you'll look at how to manage a missing value and how to delete missing values. Missing value treatment is an important task in standard data mining literature. In the R programming language, missing values are represented as NA. NAs are not string or numeric values. They're considered as an indicator for missing values. After importing a dataset into the R programming platform, it's important to check whether, for any variable, missing values exist or not. To check that, the is.na command is used. Consider this example. Object x is a numeric vector that contains some na values to verify that is.na can be used. Whether it is satisfied, the result would be true. If we compute anything with the presence of na, we end up getting an error or no result. Either we can replace the dataset by altering the na values, or we can remove those na values while performing any computation. Now we can also use na.rm parameter to set equals true, so that we get the result and no error. .na.rm equals t, that is used to remove the NAs from the mean computation for object X. Missing value imputation techniques. To delete missing values from the dataset, na.omit can be used. It removes the entire row even if the data is missing for a single variable. There are various missing value imputation methods. Mean imputation. The missing values in a data vector is replaced by the mean or median value of that vector, excluding the NA. Local average method. Taking the local average for the missing value by taking into account 3 or 5 periods moving average. That is, for a 3 period, the average of missing data, prior value and posterior value can decide what the missing value should be. Keeping that separate. Sometimes the imputation is simply not possible, and maybe the client would be interested in keeping the missing values separate to understand the missing behavior separately. Model-based. There are some model-based missing value imputation techniques, such as regression-based missing value prediction method. Clustering. Similar to regression-based prediction to the missing value imputation. K-means clustering can be used to impute the missing values from the dataset. Hooray! In this video, we've learned NA and missing value management and imputation techniques. Splendid! In this section, we looked at an introduction to data mining and R with concepts, a few programming basics, R data types, and so on. You also learned importing and exporting of various external file formats using R, sorting and merging concepts, and missing data management techniques. In the next section, we're going to learn more about performing exploratory data analysis using R. Hello viewers, welcome to the first section of the course, Exploratory Data Analysis with Automobile Data. In this section we'll learn to use basic statistics to know properties of a single and multiple variables. We'll also learn to calculate correlation and association between 2 or more variables. You'll be performing multivariate data analysis and applying statistical tests on data to conclude hypotheses. Now we move on to the first video of this section, Univariate Data Analysis. In this section we're going to use 2 datasets, diamonds.csv and cars93.csv, and then use describe function to get a better understanding of the data description. Finally, we'll use skewness and boxplot to understand the shape of a distribution for a variable. To generate univariate statistics about a dataset, we have to follow 2 approaches, one for continuous variables and the other for discrete and categorical variables. Univariate statistics for continuous variables include numerical measures such as averages, mean, variance, standard deviation, quantiles, median, quartiles, and so on. The mean represents each and every point in the dataset. The variance indicates the fluctuation, deviation of the individual data points from the mean, which is the center of the distribution. Quantiles are also known as percentiles, which divides the distribution into 100 equal parts. The 10th percentile value is equal to 1 decile. The 25th percentile value is equal to the first quartile, and 75th percentile value is equivalent to the third quartile. There are other statistical measures of central tendency for understanding the univariate characteristics of a dataset. Median and mode are also referred as positional values, but still mode can be looked at for a continuous variable to check whether it's a bimodal series. In case of bimodal series, it's difficult to compute the center of the distribution. For original data or rank data calculation of mean, representation is a good idea. It's always suggested to represent univariate statistics using median or mode. Comparison of mean, median and mode values along with skewness, kurtosis and standard deviation gives a clear value about the shape of the data distribution. All of these measures of central tendency and measures of dispersion together can be calculated using a single command, and also using different individual commands. Here we're going to use 2 datasets, diamonds.csv and cars93.csv. Both belong to 2 libraries that are inbuilt in the R software for practical demo purposes. Let's import the required datasets. We first imported cars93 dataset. You can also do it using read.csv function. Let's use a few commands in R to understand the data better. We'll print the names in car dataset. As you can see, the cars93.csv dataset has 28 variables and 93 observations. The variable type can be printed using the str function. You can see the 28 variables, 93 observation, and variable types for every variable in the output. Calculating the univariate statistics for a few continuous variables like price, mpg.city, and mpg.highway, and discrete variables like type, airbags, and manual transmission available can be displayed here. You can practice the rest of the variable to get a complete understanding of the dataset. The max command estimates the maximum value for a variable, whereas min command computes the minimum value. The sum calculates the total of all the values. The mean function calculates the arithmetic averages of the values. The median function calculates the median value, and range calculates the vector of min and max. The VAR command computes the sample variance, and COR command correlation between two vectors. Rank command calculates the vector of the ranks of the values in a vector. The quantile function computes a vector containing the minimum, lower quartile, median, upper quartile, and maximum of a vector. We'll now be using the summary function for univariate. For the price available, you can see the minimum value, the first quartile median value, mean value, third quartile, and maximum value. We'll now calculate for mpg city variable. You can see the statistics on the screen. Similarly, do it for mpg.highway, type, airbags, and manual transmission. We'll take a look at the output of summary function of dataframe. As you can see, for a continuous variable, the numerical measures of central tendency are computed, and for a categorical variable, the class frequencies are computed. Let's take a look at summary of Cars 93 data on the whole. You can see the output. The summary command for continuous variables such as RPM, horsepower, and so on shows the minimum, first quartile, mean, median, third quartile, and maximum values. The univariate statistics for the categorical variable are car type, airbags, manual transmission availability, and so on, are represented as frequency tables. The class that has the highest frequency is considered to be the modal class. Similar summary statistics can be generated using functions such as 5num function and describe function, which provides more information than the summary function. Let's use 5num function for price variable, and you can observe that the same output is generated as summary function. We'll now use 5num for other variables too, and you can see we get the same output. Let's use the describe function from the library HMISC. We'll now import the library as shown. It is loaded with warning messages, and we'll use describe function as we did using summary function. It shows the whole summary of dataset. As you can see, it has 28 variables and 93 observations. The output is the same as the summary function. The univariate summary statistics can also be calculated using the apply function. The univariate statistics gives us an impression about the shape of the distribution. Now we'll create one variable for numeric data and another for categorical data. After using the apply function, you can see that it's giving a minimum price, maximum price, and mpg city. To understand the shape of a distribution for a variable, we can use skewness and boxplot. We can also use the skewness function, which is available in library E1071. We'll first load the library using the library function and use skewness attribute and see the output. We can create a custom function for measuring skewness, and that along with the apply function. Now we'll create a skewness function and execute it and use apply function on the same. As you can see, the same output is generated. So, what is skewness? Skewness is known as a measure of symmetrical distribution, where the value of skewness indicates whether a distribution is positively skewed or negatively. When the value of skewness approaches 0 or is close to 0, it indicates that the distribution is symmetric and the mean, median, and mode are exactly the same. When the value of skewness is less than 0, it indicates the value of the mean is less than the mode. And this is because of availability of extreme values on the negative side of normal distribution. When the value of skewness is greater than 0, it indicates that the value of the mean is greater than the mode. And this is because the availability of extreme values on the right-hand side of the normal distribution. Since identification of outliers and their removal is very important, the measure of skewness helps in that direction. But that is not the only way to figure out outliers. There are other methods such as box plot and other custom outlier detection formulas. If we look at the previous 3 variables, it implies that there are indications that outlier values may exist on the positive side of the normal curve for price, mpg.city and mpg.highway variables, because the skewness value is greater than 0. To verify the existence of outliers, we can take a box plot and print the outliers. You can see that using box plot command, you can see the box plot is created for price, mpg city and mpg highway. Great! In this video, you've learned univariate data analysis. In the next video, you'll learn about bivariate analysis. Hello, welcome to the next video of this section, bivariate analysis. In the previous video, you learned about univariate analysis. In this video, we're going to know the bivariate relationship between 2 numeric values. We'll check if the variables are categorical or continuous and build the plot. The relationship or association between 2 variables is known as bivariate analysis. There are 3 possible ways of looking at the relationship. First one is numeric to numeric relationship. The next is numeric to categorical relationship. And the last one is categorical to categorical relationship. To know the bivariate relationship between 2 numeric values, typically a scatter plot is used if the 2 variables happen to be continuous, and a bar plot is used if one variable is categorical and the other is continuous. Let's import some libraries, ggplot and gridextra. The libraries are imported with some warning messages. Now, plot the graph using the code shown on your screen. The ggplot function is used to get the plot. You can see that the plot is showing the relation between price and mileage within a city for different cars. Similarly, the relationship between price and highway mileage can be represented using a scatter plot as well. This is the line of code to do that. Here you can see the relationship between price and mileage on highways. The numeric, categorical and 2 categorical relationships will be explained in the next section, Visualize Diamond Dataset, in detail. Cool! In this video, we've learned about bivariate analysis. In the next video, we'll learn about multivariate analysis. Hello viewers, welcome back to the next video of this section, multivariate analysis. In the last video, you learned about bivariate analysis. In this video, we're going to take a look at multivariate relationships between more than 2 variables. The multivariate relationship is a statistical way of looking at multiple dependent and interdependent variables and their relationships. Here we'll talk briefly about multivariate relationships between more than 2 variables. Multivariate relationships between various variables can be known by using correlation method as well as cross-tabulation. Let's see the correlation between the variables using the pairs function. You can see the correlation plot. This plot summarizes the strength of the linear relationships between each pair of response variables. Here they are price mpg city and mpg highway using the correlation plot. In this video, you've learned about multivariate analysis. In the next video, you'll understand distributions and transformation. Hello viewers, welcome to the next video of this section, Understanding Distributions and Transformation. In the previous video, you learned multivariate analysis. In this video, we're going to take a look at normal, binomial, and Poisson probability distribution. Understanding probability distributions is important in order to have a clear idea about the assumptions of any statistical hypothesis test. For example, in linear regression analysis, the basic assumption is that the error distribution should be normally distributed, and the variables relationship should be linear. Hence, before moving to the stage of model formation, it's important to look at the shape of the distribution and types of transformations that one may look into to make the things right. This is done so that any further statistical techniques can be applied on the variables. The concept of normal distribution is based on central limit theorem, CLT, which implies that the population of all possible samples of size n, drawn from a population with mean, mu, and variance sigma, approximates a normal distribution with mean mu and sigma divided by n when n increases towards infinity. Checking the normality of variables is important to remove outliers so that the prediction process does not get influenced. Presence of outliers not only deviates the predicted values, but would also destabilize the predictive model. We'll see some sample code and examples show how to check the normality graphically and interpret the same. To test out the normal distribution, we can use the mean, median, and mode for some of the variables. Here we'll be calculating for price. You can see the mean is 19.5. We'll now calculate median, standard deviation, variation, and skewness of price variable. We'll now plot the data using ggplot. From the plot, we can conclude that the price variable is positively skewed because of the presence of some outlier values on the right-hand side of the distribution. The mean of the price variable is inflated and greater than the mode because the mean is subject to extreme fluctuations, which can be observed in plot. Now let's try to understand a case where normal distribution can be used to answer any hypothesis. Suppose the variable mileage per gallon on a highway is normally distributed with a mean of 29.08 and a standard deviation of 5.33. What is the probability that a new car would provide mileage of 35? We can calculate it using the p-norm function. You can see that the required probability that a new car would provide mileage of 35 is 13.36%, since the expected mean is higher than the actual mean. The lower tail is equivalent to false, which you can see here. Let's see about binomial distribution. Binomial distribution is known as discrete probability distribution. It describes the outcome of an experiment. Each trial is assumed to have only two outcomes, either success or failure, either yes or no. For instance, in the Cars 93 dataset variable, whether manual transmission is available or not is represented as yes or no. Let's take an example to explain where binomial distribution can be used. The probability of a defective car given a specific component is not functioning is 0.1%. You have 93 cars manufactured. What is the probability that at least one defective car can be detected from the current lot of 93? This can be found out using the p-binom function given the number of defective cars and total number of cars and probability. So the required probability that a defective car can get identified in a lot of 93 cars is 0.0006, which is very less, given the condition that the probability of a defective part is 0.10. This is all about a binomial distribution. We'll now learn about Poisson distribution. Poisson distribution is for count data where, given the data and information about an event, you can predict the probability of any number occurring within that limit using the Poisson probability distribution. Let's take an example. Suppose 200 customers, on average, visit a particular e-commerce website portal every minute. Then find the probability of 250 customers visiting the same website in a minute. This can be done using PPOIS function, where we are specifying the number of expected customers, average number of visits, and lower tail. As you can see, the required probability is 0.0002, which is very rare. Apart from the aforementioned common probability distributions, which are used very frequently, there are many other distributions that can be used in rare situations. In this video, you've learned about distribution and transformation. In the next video, you'll learn about interpreting distributions and variable binning. Hi, you're watching the section's next video, Interpreting Distributions and Variable Binning. In the previous video, you learned distributions and transformation. In this video, we're going to interrupt the different types of distribution and learn about variable binning. Calculation of probability distributions and fitting data points specific to various types of distribution and subsequent interpretation help in forming a hypothesis. That hypothesis can be used to estimate the event probability given a set of parameters. Let's take a look at the interpretation of different types of distributions. We'll first take a look at interpreting continuous data. The maximum likelihood estimation of the distributional parameters from any variable in a dataset can be known by fitting a distribution. The density function is available for distributions such as beta, Cauchy, chi-squared, exponential, f, gamma, geometric, log normal, logistic, negative binomial, normal, Poisson, t, and Weibull. These are recognized cases being ignored. For continuous data, we'll be using normal and t distributions. To use the fit_distr function, we first need to import it. Once that's done, we're creating x variable using fit_distr function. In the code, we have taken the mpg.highway variable from the cars93 dataset and density function is t. We'll obtain the parameter estimates, the estimated standard deviation, the estimated variance-covariance matrix, the log likelihood value, as well as the total count using the code 1 by 1. Similar activity can be formed by fitting a normal distribution to the continuous variable. Here we'll just change the density function to normal. And calculate the parameter estimates, the estimated standard deviation, the estimated variance-covariance matrix, the log likelihood value, and total count. Now we're going to see how to graphically represent the variable normality. We'll use the function QQnorm and QQline to get the graph. You can see that the deviation of data points represented as circles are distance from the straight line t. Let's now interpret the discrete data, as all the categories are in it. Let's take the type variable of cars93 dataset and print the table. We'll now calculate the frequency using this line of code. Next, we'll calculate relate frequency with this code. Let's give option and print our real frequency. We'll calculate the C-bind, as you can see both frequency and related frequency. To visualize this graphically, we need to represent it through a bar plot using this function. You can the bar graph with layers and title distribution of categorical variable. The continuous variable is the most appropriate step that one needs to take before including the variance in the model. The continuous variable is the most appropriate step that one needs to take before including the variable in the model. This can be explained by taking one example, fuel tank capacity, of a car from the cars93 dataset. Based on the fuel tank capacity, we can create a categorical variable with high, medium, and low, lower medium. This is the code for creating range, and you can see the min and max value. Print it using the cat function. Let's create options for this and digits as 2 and print the t variable. The range of fuel tank capacity is identified as 9.2 and 27.0. Then, logically, the class difference of 4 is used to arrive at classes. Those classes define how each value from the variable is assigned to each group. The final outcome table indicates that there are 4 groups. The top fuel tank capacity is available on 4 cars only. Variable binning or discretization not only helps in decision tree construction, but is also useful in the case of logistic regression mode and any other form of machine learning based models. In this video, we've learned about interpreting data and variable binning. In the next video, you'll learn about contingency tables, bivariate statistics, and checking data normality. Hello, we're back with the next video of this section. Contingency tables, bivariate statistics, and checking for data normality. In the previous video, you learned to interpret distributions and variable binning. In this video, we're going to see contingency tables, bivariate statistics, and checking for data normality using the cars93 dataset. Contingency tables are frequency tables represented by 2 or more categorical variables, along with a proportion of each class represented as a group. Frequency table is used to represent one categorical variable. However, contingency table is used to represent 2 categorical variables. Let's see an example to understand contingency tables, bivariate statistics, and data normality using the cars93 dataset, which is already loaded here. The individual frequency table for 2 categorical variables, airbags and type of the car, are represented here. We'll create a cont table using this code and print it. You can see that the cont table object holds the cross-tabulation of two variables. A portion of each cell in percentage is reflected in the table. If we need to compute the row percentages or column percentages, then it's required to specify the values in the argument. Let's do this by proposition function as shown on your screen. For row percentages, the value needs to be 1, and for column percentages, the value needs to be entered as 2 as shown on the screen. Let's take a look at the summary of contingency table using this code. The summary of the contingency table performs a chi-square test of independence between the two categorical variables. The chi-square test of independence for all factors is represented here. The message that the chi-squared approximation may be incorrect is due to the presence of null or less than 5 values in the cells of the contingency table. I equals n in this case. Two random variables, car type and airbags, can be independent if the probability distribution of one variable does not impact the probability distribution of the other variable. The null hypothesis for the chi-square test of independence is that two variables are independent of each other. Since the p-value from the test is less than 0.05 at 5% level of significance, we can reject the null hypothesis that the two variables are independent. Hence, the conclusion is that car type and airbags are not independent of each other. They are quite related or dependent. Instead of two variables, what if we add one more dimension to the contingency table? Let's take origin. And then the table would look like this. The summary command for the test of independence of all factors can be used to test out the null hypothesis. Let's create a summary of new contingency table, and you can see the output on the screen. Apart from the graphical methods discussed previously, there are some numerical statistical tests that can be used to know whether a variable is normally distributed or not. There is a library called norm.test for performing data normality tests. A list of functions that help in assessing the data normality from this library are: let's apply the normality test on the price variable from the Cars 93 dataset. First, we'll import the library. Before that, we've got to install the package. Cool, let's use it now. We'll now use ad.test, also known as Anderson-Darling test, to calculate normality of data. And this is the code for Kramer-von Mises test. Let's use the code for Pearson chi-square test for normality. And Shapiro-Frankia test for normality. It's evident that the price variable is not normally distributed, as the p-values from all the statistical tests are less than 0.05. If we add more dimensions to the bivariate relationship, it becomes a multivariate analysis. Let's try to understand the relationship between horsepower and length of car from the Cars 93 dataset. We'll import package coreplot from library and then create a variable O, which holds the correlation between horsepower and length dataset. And finally, plot the correlation plot. When we include more variables, it becomes a multivariate relationship. Let's try to plot a multivariate relationship between various variables from the Cars 93 dataset using this code. You can see the correlation plot using ellipse method. There are various methods that can be passed as an argument to the correlation plot. They are circle, square, ellipse, number, shade, colour and pi. In this video you've learned contingency tables, bivariate statistics and checking for data normality. In the next video you'll learn about hypothesis testing. Hello, welcome to the next video of this section, hypothesis testing. In the previous video you learned about contingency tables, bivariate statistics and checking for data normality. In this video we're going to take a look at hypothesis testing procedures to test out the population mean. The null hypothesis states that nothing has happened. The means are constant and so on. However, the alternative hypothesis states that something different has happened and the means are different about a population. There are certain steps in performing a hypothesis test. The first step is to state the null hypothesis. A statement about the population is assumed. For example, the average mileage of cars within a city is 40. Next, you have state the alternative hypothesis. If the null hypothesis turns out to be false, then what other possibility is there? For example, if the mileage within the city is not 40, then it is greater than 40 or less than 40. If it's not equal to 40, then it is a non-directional alternative hypothesis. Then, calculate the sample test statistic. The test statistic could be t-test, f-test, z-test, and so on. Select the appropriate test statistic based on the data availability and the hypothesis declared previously. Decide the confidence limit. There are three different confidence limits: 90%, 95% and 99%, depending on the degree of accuracy related to a specific business problem. It's up to the researcher, analyst, to choose the level of confidence interval. 5. Define the alpha value. If the confidence level selected is 95%, the alpha value is going to be 5%. Hence, deciding the alpha value would help in calculating the p-value for the test. The final one is decision. If the p-value selected is less than the alpha level, then there is evidence that the null hypothesis can be rejected. If it's not, then we're going to accept the null hypothesis. Using the hypothesis testing procedure, let's take an example from the CARS 93 dataset to test out the population mean. One-tailed test of mean with known variance. Suppose the researcher claims that the average mileage given by all the cars collected in the sample is more than 35. In the sample of 93 cars, it's observed that the mean mileage of all cars is 29. So, should we accept or reject the researcher's claim? Now let's see how we'll decide this. Consider the mean of null hypothesis as 35, and the alternative hypothesis mean is greater than 35. Let's calculate the mean of MPG highway of the CARS 93 dataset. As you can see, the mean is 29.08. Next, we'll calculate standard deviation and store it as sigma. And the standard deviation is 5.33. Now we'll calculate the length using the code, and the output is 93. We'll create a variable x-bar, which is equal to 35, and then calculate z and print it using this code. And we get it as 10.69. We will calculate the alpha value and calculate the critical value at 5% alpha level. For that we need to set alpha at 0.5, that is 95% accuracy level. Let's calculate Z1 using Q-normality function, and it's 1.64. We'll conclude it using if-else statement. You can see that we need to reject the null hypothesis as the mean is less than 35. This was for one-tailed test of proportions. Let's calculate for two-tailed test of variance. Suppose null hypothesis is 35 and the alternative hypothesis mean is less than 35. We'll now again calculate all the variables that we calculated earlier. The error here occurred due to the extra parenthesis, which has been rectified. We'll combine minus z1 and z1 and finally use if-else function. Suppose z is greater than z1, then it will reject null hypothesis, and if z is less than minus z1, then it will accept the null hypothesis. Thus, we've analysed one-tail and two-tail test of population mean for the sample data for known variance. One-tail and two-tail test of proportions. Using the CARS 93 dataset, Suppose 40% of the USA manufactured cars have an RPM of more than 5,000. From the sample data, we found 17 out of 57 cars have RPM above 5,000. What do you interpret from this context? We'll calculate mileage from subset function and RPM variable of cars 93 dataset. Let's print the table of origin variable of mileage. Next, we'll calculate P1 value, that is division of 17 by 57. Then define a variable P0, which holds the value of 0.4. And then count of mileage variable and calculate Z value as shown. Let's calculate critical value at 5% of alpha level using the same code and then calculate Z1 using qnorm function. Lastly, use if-else function like we did previously. If Z is greater than Z1, it will reject the null hypothesis, else it will accept it. If the alternative hypothesis is not directional, it's a case of two-tailed test of proportions. Nothing from the above calculation would change except the critical value calculation. So again, we'll be using the same steps as we did. Here we'll combine Z1 and minus Z1, and then use two conditions in if-else function. If Z is greater than Z1, it will reject the null hypothesis. And if Z is less than minus Z1, it will accept null hypothesis. In the output, you can see that since Z is less than minus Z1, two-sample paired test for continuous data. The null hypothesis that is being tested in the two-sample paired test would be that there is no impact of a procedure on the subjects, the treatment has no effect on the subjects, and so on. The alternative hypothesis would be that there is a statistical significant impact of a procedure effectiveness of a treatment or drug on the subjects. Though we don't have such a variable in the Cars 93 dataset, we can still assume the paired relationship between minimum prices and maximum prices for different brands of cars. Null hypothesis for the two-sample t-test. There is no difference in the mean prices. Alternative hypothesis. There is a difference in the mean prices. Come, let's calculate this using this code. As you can see, the p-value is less than 0.05, hence it can be concluded that the difference in mean minimum price and maximum price is statistically significant at alpha 95% confidence level. Next is two-sample unpaired test for continuous data. From the Cars 93 dataset, the mileage on the highway and within the city is assumed to be different. If the difference is statistically significant, it can be tested by using the independent samples t-test for comparison of means. For this null hypothesis, there is no difference in the MPG on a highway and MPG within the city. And for the alternative hypothesis, there is a difference in the MPG on highway and MPG within city. So we'll use two samples t-test. When the two samples are independent, from the output, the p-value is less than 0.05. Hence, we can reject the null hypothesis that there is no difference in the mean mileage on the highway and within city. There is a statistically significant difference in the mean mileage within the city and on the highway. This can be represented in a slightly different way by putting a null hypothesis is the mean mileage difference within the city is different for manual versus automatic cars. This can be done using this code. So, we can conclude that there is a statistically significant difference in the mean mileage between automatic and manual transmission vehicle types. This is because the p-value is less than 0.05. Before applying t-test, it's important to check the data normality. Normality of a variable can be assessed using the Shapiro test function. Now let's calculate the plot using the hist function. Then plot it using the QQ line function. Looking at the QQ plot for the lineage per gallon within city and the histogram, it can be concluded that the variable is not normally distributed. Since the mileage variable is not normally distributed, it's required to apply non-parametric methods such as Wilcoxon's signed rank test or Kolmogorov's Smirnov test. Next, we'll look at two-sample variance test. To compare the variances of two samples, f-test is used as a statistic, which is done using this code. Since the p-value is less than 0.05, we can reject the null hypothesis, is that there is no difference in the variance of mileage on a highway for manual and automatic cars. This implies there is a statistically significant difference in the variance of two samples at 95% confidence level. The variances of the two groups can also be tested using the Bartlett test, and this is the corresponding code. From the test, it can be concluded that the null hypothesis of equal variances can be rejected at alpha 0.05 level, and it can be proven that there is a statistically significant difference in the variance of the two samples. One-way ANOVA. Here, the variable considered is RPM, and the grouping variable considered is cylinders. Null hypothesis. Here, there is no difference in the means of RPM across different cylinder types, and in alternative hypothesis, there is a difference in the mean RPM for at least one cylinder type. Let's calculate AOV. From the ANOVA output, you can see the p-value is less than 0.05, hence the null hypothesis can be rejected. That means for at least one cylinder type, the mean RPM is statistically significantly different. To identify which cylinder type is different, a post hoc test can be performed on the results of the ANOVA model using this code, where we've used the Turkey HSD function. Here, wherever the p-adjusted value is less than 0.05, the mean difference in RPM is statistically significantly different from other groups. Let's look at two-way ANOVA with post hoc tests. The factors considered are origin and airbags. The hypothesis that needs to be tested is there any impact of both the categorical variables on the RPM variable? You can see the output here. Let's calculate OST hoc test on this using Turkey HSD function, and you can see the corresponding output. This is all about the hypothesis testing. Great! In this video you learned about hypothesis testing. In the next video we'll learn about non-parametric methods. Hello, we're back with the final video of this section, non-parametric methods. In the previous video you learned about hypothesis testing. In this video you'll learn about Wilcoxon signed rank test, Mann-Whitney-Wilcoxon test, and Kruskal-Wallis test. When a training dataset does not conform to any specific probability distribution because of a non-adherence to the assumptions of that specific probability distribution, the only option left to analyze the data is via non-parametric methods. Non-parametric methods do not follow any assumption regarding the probability distribution. Using non-parametric methods, one can draw inferences and perform hypothesis testing without adhering to any assumptions. Now let's look at a set of on-parametric tests that can be used when a dataset does not conform to the assumptions of any specific probability distribution. The first test is the Wilcoxon signed rank test. If the assumption of normality is violated, then it's required to apply non-parametric methods in order to answer a question, such as, is there any difference in the mean mileage within a city between automatic and manual transmission type cars? Let's see this. This is the code to do that here. We have taken the MPG City and Man Trans available from the Cars 93 dataset, and this is the output. The argument paired can be used if the two samples happen to be matching pairs and the samples do not follow the assumptions of normality. If we use paired as t, then you can see this output. Next is Mann-Whitney-Wilcoxon test. If two samples are not matched, are independent, and do not follow a normal distribution, then it's required to use Mann-Whitney-Wilcoxon test to test the hypothesis that the mean difference in the two samples are statistically significantly different from each other. This is the code, and you can see the output on the screen. Kruskal-Wallis test. To compare means of more than two groups, that is, the non-parametric side of ANOVA analysis, we can use the Kruskal-Wallis test. It's also known as a distribution-free statistical test. This is the code for the test. Thus, you can see that you can apply all non-parameters to calculate the assumptions of any probability distribution. In this video, you've learned the non-parametric methods. In this section, we discussed various statistical tests, their syntax, interpretations, and situations where we can apply those tests. In the next section, we're going to use some inbuilt datasets with different libraries to create intuitive visualizations. Hello, welcome to a new section of our video course, Visualize Diamond Dataset. In the previous section, we saw exploratory data analysis with automobile data. In this section, we'll learn data visualization using ggplot2 and create different types of charts, plots, and histograms. We'll then see how to use Plotly. And finally, we'll create geomapping. Now we move on to the first video of this section that will give you an in-depth introduction of different data visualization options we have to represent our data. In this video, we'll use the ggplot function, change colors, themes, and size, and experiment variations with the scatterplot. Every data mining project is incomplete without proper data visualization. While looking at numbers and statistics, it may well tell a similar story for the variables we are looking at by different cuts. However, when we visually look at the relationship between variables and factors, it shows a different story altogether. Hence, data visualization tells you a message that numbers and statistics fail to do that. From a data mining perspective, data visualization has many advantages, which can be summarized in 3 important points. Data visualization establishes a robust communication between the data and the consumer of the data. It imprints a long-lasting impact, as people may fail to remember numbers, but they do remember charts and shapes. When data scales up to higher dimension, representation in numbers does not make sense, but visually it does. In this section, you'll get to know the basics of visualization, along with how to create advanced data visualization using existing libraries in R programming language. Typically, data visualization approach can be addressed in 2 different ways. What do you want to display to the audience? Is it comparison, relationship, or any other functionality? How do you want to display the insights? Which one is the most intuitive way of chart or graph to display the insights? Based on the preceding 2 points, let's have a look at the data visualization rules and theories behind each visualization. And then we're going to look at the practical aspect of implementing the graphs and charts using R script. So, from a functional point of view, these are the graphs and charts which a data scientist would like the audience to look at to infer the information. Here we have segregated different graphs and charts based on their usage. This will help you take the right decision. Let's look at each of them. The first situation is where you need to do comparisons between variables. Basically, when it's needed to represent 2 or more categories within a variable, then these charts are used. That is, bar chart, box plot, bubble chart, etc. Then we have testing or view proportions. It's used when there is a need to display the proportion of contribution by one category to the overall level. These are the charts and graphs you could use for this purpose. There may be instances where you want to render a relationship between variables. Association between 2 or more variables can be shown using scatterplot, bar chart, radar chart, etc. When it's required to display the order in the variables, such as a sequence of variables, then tree diagram and tree map. When a dataset contains the geographic location of different cities, countries and states' names, or longitudes and latitudes, then the following charts can be used to display visualization, and then bubble map. Geomapping, dot map, and flow map are used. When you're required to display constituents of a variable and the contribution of each category level towards the overall variable, then the following charts are used: pie chart, stacked bar chart, donut chart. In order to understand the variation in a variable across different dimensions, represented by another categorical variable, box plot, bubble chart, histogram, stem, and leaf plot are used. For pattern recognition and relative importance of data points on different dimensions of a variable, these charts are used. The span chart, box plot, and histogram only give the spread of the data points across different bounds, so they're a good choice for these specific scenarios. Word cloud is a very interesting way of representing the textual data. You can use it for smart data visualization. Keeping in mind these functionalities that people use in displaying insights to the readers, we can see that one graph is referred by much functionality. In other words, one graph can be used in multiple functions to show the insights. These graphs and charts can be displayed by using various open source R packages, such as ggplot2, ggviz, rcharts, plotly, and Google Viz by taking one open source dataset. In the light of these mentioned 10 points, the data visualization rules can be created to select the best representation depending on what you want to represent. Relationship between 2 variables can be represented using a scatterplot. Relationship between 2 or more variables can be represented using a bubble chart. For understanding the distribution of a single variable with a few sample size, histogram is used. For understanding the distribution of a single variable with a large sample size, density plot is used. Distribution of 2 variables can be represented using scatterplot. For representation of distribution between 3 variables, 3D scatterplot is used. Any variable with a timestamp, such as day, week, month, year, and so on, can be represented using line chart. Time should always be on the horizontal axis, and the metric to be measured should always be on the vertical axis. Each graph should have a name and label so that the user does not have to go back to the data to understand what it is. In this section, we'll primarily focus on the ggplot2 library and plotly library. Of course, we'll cover a few more interesting libraries to create data visualization. The graphics packages in R can be organized as per these sequences. First is plotting, followed by graphic applications such as effect ordering, large datasets and trees, and graphs. Then we have graphic systems, devices, colors, and so on. A detailed explanation of the various libraries supporting the previous functionalities can be found at this web link. For a good visual object, we need more data points so that the density of the graphs can be more. In this context, we'll be using two datasets, diamonds.csv and cars93.csv, to show data visualization. Now let's look into data visualization using ggplot2. There are two approaches to go ahead with data visualization, horizontally and vertically. Horizontal drill down means creating different charts and graphs using ggplot2, and vertical drill down implies creating one graph and adding different components to the graph. First, we'll understand how to add and modify different components to a graph, and then we'll move horizontally to create different types of charts. Let's take a look at the dataset and libraries required to create data visualization. So, first we'll get the library ggplot. We'll import the diamonds dataset and print the columns in the diamond dataset using this command. So you can see the output now. The ggplot2 library is also known as the grammar of graphics for data visualization. The process to start the graph requires a dataset and two variables, and then different components of a graph can be added to the base graph using the plus sign. Let's get into creating a nice visualization using the diamonds.csv dataset. We start with a basic plot. So this is the line of code for creating a basic plot of color brown 4 and using the price and caret function of diamonds.csv dataset. Now let's print the graph. In this script, diamonds is the dataset and caret and price are the two variables. Using ggplot function, the base graph is created and adding points to the ggplot. The object is stored in object gg. Now we're going to add various components of a graph to make the ggplot more interesting. After creating the base plot, it's required to add title and label to the graph. This can be done using two functions, ggtitle or labs. So let's add the title first and click on Run. Now we use labs to obtain the same plot and we add the code for it. As you can see, we get the same output for ggtitle and labs functions. Then, let's add a theme to the plot for customizing text element. Now we've added the theme function at the bottom of our script. Currently the graph looks a little congested. To make the graph more intuitive, we need to add labels to the X and Y axis, removing ticks and text from any axis to make the graph more clear. Rotating the text in any axis is required when the row name or column name contains text or a large number which is difficult to read in full length. Let's add a few lines of code to make our graph more intuitive. So we add labels to the graph, and let's run it. As you can see, the label is changed to price by caret. Now let's try removing text and ticks from an axis. As you can see, the text and ticks from the y-axis are removed through the code we just added. Now let's see how we can rotate the text in an axis. This is the line of code to do that. As you can see here, the text of the x-axis is rotated by 50 degrees. Next, we step ahead to add color to the axis name. We add this line of code at the bottom of the script and run to check the output. As you can see, we have changed the color of x-axis elements to chocolate color and the y-axis colors to brown. In order to focus on any specific portion of the plot, the x-axis limit and y-axis limit can be changed. Let's add a few lines of code for it. Now, you can see in the console the number of rows removed while executing the limit on both the axes. If both x-axis and y-axis represent continuous data, any third variable as a factor can be introduced to the ggplot object to set legends and look at the data, how it is distributed across the factor variable. Let's see how we can set legends in the graph. So, this is the line of code to add cut as the factor to the ggplot. As you run the script after adding this line of code, you can see the cut factor has been added. Now let's add another factor called color. As you run the script now, you can notice the change in the graph. Let's add another factor called clarity. Again, the graph has changed with the clarity factor. Awesome. Now we step further to add the legend title. After adding this line of code, when you run the script, you'll notice that there is no title in the plot. Now let's have a look at how we can change the title name of the legend. We add these lines of code at the bottom of our script. So here we have changed the value for legend.title, color and size along with the clarity. Let's check the output. As you notice now, the title has changed to by. Clarity, the color is dark blue and the font size is 16. Now let's see how we can change the background boxes of the legend. Cool. We've changed the background boxes to dogger blue. Now we modify the size of the symbols used in the legend. Add this line of code and run the script. You can observe the size of the circles have increased to size 4. In addition to the previous visualization, it's required to connect the scatter plots and change the background. Add lines to the scatter plot in order to understand the sequence R pattern that exists between the variables which are related. Let's add code for this to our script and run. You can see that lines have been added to our scatter plot. Another important aspect of data visualization is how to display multi-dimensional cuts in a plot. For example, in the diamonds dataset, we're currently looking at the relationship between the price of the diamond and the carat it contains. There are 3 more variables, which are cut, color, and clarity. It makes sense to understand if the relationship is consistent across these 3 variables. That means understanding if we can plot the relationship between carat and the price of the diamond by different cut, different color, and different clarity categories. Let's look at the distribution of the 3 categorical variables. Let's print the table of the 3 categorical variables and add lines of code for it and run it. So you can see the output in the console. Let's add a multi-variable cut to the graph. Now we run the script. In the graph, the cut variable is used to show the relationship between the carat and the price. The number of rows selected is 4 to represent the graphs in a clear manner. If we add one more variable to the cut variable, that is clarity, the graph would be more intuitive and insightful. So let's do it right now. We add the code for it and run the script. So you can see that we obtained a better plot with which is more insight. While creating the graphs using a multi-dimensional cut variable, it's not necessary that all the graphs would be on the same scale. In automatic mode, these scales become a standard for all the plots. Hence, sometimes certain plots get compressed. Thus, it's required to make the graphs scale-free in order to rearrange the scales based on observed values. So, this is a line of code for it. With this, we can scale free graphs in multi-panels. Let's run and see the output. Here's the output for the facet wrap function. Using the facet grid option, we can display the bivariate relationship between 2 categorical variables using the ggplot2 library. Let's add the code for this and run our script again. Wait a second, let me enlarge it so we can have a closer look. Now, there are certain external graphical themes which can be imported to the ggplot2 function for visualization, such as library ggthemes. Before we move ahead, let's import this library. You need to install ggthemes. You can do this using the install package utility of RStudio, as you can see here. OK, the ggthemes package is installed. Let's run this so that it's loaded. Instead of this, you can also use Tableau, which is a tool known for data visualization. Its color and themes can also be used along with ggplots. Let's try to change the discrete category colors. We've added these lines at the bottom of our script. As you run the script now, you can notice the change in the colors, which we did using the color factor cut. Next, we use a Tableau color. We've already imported the library ggthemes, and let's use the Tableau color with the help of scale color Tableau function. Now, run the script and we can observe the change in color in the output. Plots created can be slightly modified using the colour gradient and plotting a distribution on the graph itself. Let's use the colour gradient and add the code for it to our script. When we run this, we obtain the changed output. Let's plot a distribution on the graph. First, we need to calculate the mean of the price. Here we use the mean method for it. Next, we add plotting distribution on the graph using the mid, that is, mean of the price variable of the diamond dataset. Having discussed in depth about the components in a graph building process, now let's try to understand how to create different charts and graphs using ggplot2.qplot function is a basic plotting function in ggplot2, which is a wrapper for creating different types of plots. There are two options for a user, either go plotting with the qplot or ggplot function. Though it was quite long, but it was amazing. In this video we had an introduction to ggplot and the various plots and graphs used for data visualization. In the next video we'll explore about visualizing charts, histograms and geomapping. This is the second video of this section, visualizing charts, histogram and geomapping. In the previous video we looked at the introduction of ggplot and data visualization. In this video we create bar chart, box plot, bubble chart and donut chart with the cars93.csv dataset. We'll also visualize geomapping using the Google Visualization Library in R. Bar charts are preferred as a method of visualization for the categorical variables, also used to represent the count or percentage of each group. The horizontal axis represents the categories and the vertical axis either represents the count or the percentage. Let's create a bar chart using the cars93 dataset. This is the line of code to create the bar plot of the type variable for the car93 dataset. Now we run the script, and here you can see the bar plot with the category on the x-axis and the count on the y-axis. Next, we have box plot. It's not only easy to interpret box plots using the ggplot package, but also easy to customize the plot. One can easily recognize the outliers imposed on each of the corresponding box plots. Let's add the code for it. Here we use the type and price of the cars93 dataset, and now we print the box plot. We've obtained the box plot with the type on the x-axis and the price on the y-axis. Now we move on to bubble charts. The bubble chart belongs to the family of the scatter plot. It's preferred when it's required to represent three quantitative variables. Two quantitative variables are represented on two axes, and one quantitative variable is used to represent the size of each bubble in a bubble chart. Let's add the code in our script to create a bubble chart. In the output you can see the engine size on the x-axis and the MPG city on the y-axis, while the bubbles represent the size of the prize. After this comes the donut chart. Donut chart is used in place of pie chart when the number of categories exceeds 5. Here we add the code to plot the donut chart and click on Run. As you see in the output, we obtain the donut chart. In the code we've used the cylinders and max price variables of the cars93 dataset. Lastly, we have geomapping. Any dataset that has a city name and state name or a country name can be plotted on a geographical map using Google Visualization Library in R. Using another open source dataset, state.x77 inbuilt in R, we can show how a geomap looks. The Google Visualization Library, using Google Maps API, tries to plot the geographic locations on the plot along with the enterprise data. It publishes the output in a browser which can be stored back as an image to use further. First, we need to import the Google Viz library, and then we install it. After the installation, let's load it again. Now we use the state.x77 dataset and print this dataset. Once you run the script, you can now see the state.x dataset printed in the console. Then we create two variables, say states, using this line of code. Let's run to check the output. Next, we need to use the gmap. So, you can see that we're creating a Google map, and this is the code for it. We've used here states. Then we plot the gmap using the plot function. As you run the script now, you'll be directed to the browser, and here's a map for the state.x77 dataset. In this video, we've learned to visualize charts, histogram and geomapping. In the next video, we'll move further and dive into visualizing scatterplot, word cloud and more. Visualizing scatterplot, word cloud and more. Previously, we saw how to visualize charts, histograms and geomapping. In this video, we'll create histograms along with other charts like line charts, pie charts, scatter plots, and stacked bar charts. We'll also create stem and leaf plots. We'll then move ahead for creating word cloud and coxcomb plots. Let's start with histogram. This is probably the easiest plot that every data mining professional must be doing. So let's see how we can create a histogram using the ggplot library. This is the line of code we've added to create the histogram. So here we've used the ggplot, GOM, histogram, and ggtitle. We'll fill the histogram with Firebrick. Let's run this code. As you can see, we have RPM on the x-axis and count on the y-axis. Next, we have line chart. Line chart is not a preferred chart while showing raw data. However, it's important while showing some variations across different categories relating to some metric. Though it's not a preferred chart, but it depends on the practitioner how he or she wants to display and tell a story to the reader. Add these lines of code to create a line chart and run this. As you can see, we got the line chart with the RPM on x-axis and price variable on the y-axis. Next is the pie chart. A pie chart is a representation of categorical values when the label for each categorical value is less than 10. If it exceeds 10, then it's suggested to look at a histogram or bar plot for comparison. Using the ggplot library, the pie chart can be created. Let's add the script to create the pie chart. Here we've taken as the factor 1 and factor type as the variables. So you can see the factor 1 on y-axis and count on the x-axis. We can also create 3D pie charts from the data frames. For that, we need to import the plottrix library using the library function. Now we create a table of the variables. Add this line of code to create separations. Then we create pie charts and also 3D pie charts. You can clearly see the difference, both the pie chart for the types of cars. One is 2D and the second is 3D. Now we move on to scatterplot. Scatterplot is a very important plot to understand the bivariate relationship that exists in data. It also shows the pattern in which the data is stored over a period of time. It's also important to show the data in a proper way while showing it in scatterplots. Let's see how a bivariate relationship can be displayed along with some third dimension dictating the visualization in a bivariate relationship. The third dimension could be a continuous variable or a categorical variable. Using the grid extra library, additional graphing window can be created where two or more plots can be represented side by side with some relationship. First, we import the grid extra library. Next, we create a scatterplot using the horsepower and mpg.highway variables of the Cars 93 dataset. Let's add a continuous variable length to scale the scatterplot points. Here we've used the color length and size as the variable. Now we display both the scatterplots in the same window. This can be done using this line of code. Let me stretch this so you can have a closer look. As you can see, the first one is the basic scatterplot, and we have added the length variable in the second scatterplot. Here, the second graph with the length variable, and which is continuous, is dictating the relationship between the horsepower and the highway mileage per gallon. The light blue coloured dots indicate lengthy cars, while the darker dots indicate smaller cars. Instead of a continuous variable, if we use a factor variable to scale the relationship between the two variables, let's see what the output is. So we create another scatterplot, SP3, with the factor of the origin as the colour. Now we add custom colour to the scatterplot SP4 using the same factor origin. Next, we do what we did previously. That is, we combine both the scatterplots, SP3 and SP4, and display both in the same window. You can easily notice the difference between the two plots. Now to display the cause and effect relationship, one needs to display a trend line or a regression line on a scatterplot. Using the ggplot library, different regression lines can be plotted, such as linear, non-linear, generalized linear, and so on. When the number of observations in a dataset is less than 1000, the lowest regression method is applied by default. However, when it's more than 1000, the generalized additive model is applied. The trend lines are displayed next. Let's create another scatterplot, and we name it as SP5. Then we add regression lines to the scatter plot. Let's display both these scatter plots in the same window. As you can see here, the first plot indicates a line graph connecting all the points, and the second plot indicates the robust linear model. Adding the generalized regression model and novice as a non-linear regression model, we can modify the scatter plots. Let's do it right now. We create another scatter plot, SP7, and run it. After this, we create one more scatter plot with the regression line. Again, we display both the scatter plots in the same window pane using this line of code. We also have 3D scatter plots, which is another addition to the line of scatter plot functions we're looking at. The 3D scatter plot library enables the users to look at the plot and rotate it to view the data points from different angles. Once executed, the script would open up a new RGL device window. Just rotate the graph and you would be able to see the data points from different angles. Let's run this line of code for it. As you can see, we got the warning since we did not install the R Command R package first. Let's install it first. After installation, we add these lines of code to create the 3D scatter plot and run the script. So, you can see the 3D scatter plot for MPG Highway, USA and non-USA. Awesome. Next, we have stacked bar chart. Stacked bar charts are just another variant of the bar charts, where more than two variables can be plotted with different combinations of colour. Let's see how we can create and make variations to it. So, we add this line of code to create a stacked bar chart with the origin and type variables of the Cars 93 dataset. We got the count on the y-axis and type variable on the x-axis. We use the same factor, that is origin. Also, we can use this line of code, which you see highlighted on the screen, to get the same output. Next comes the stem and leaf plot. A stem and leaf plot is a textual representation of a quantitative variable that segments the values to their most significant numeric digits. For example, the stem and leaf plot for the mileage within the city variable from the cars93.csv dataset can be represented as this one, which you can see in your console window. Now, to interpret the results of a stem and leaf plot, if we need to know how many observations there are which are greater than 30, the answer is 8. The digit on the left of pipe indicates items, and the numbers on the right indicate units. Hence, the respective numbers are 30, 31, 31, 32, 33, 39, 42, 46. We now move ahead to explore about an amazing data visualizing method, that is word cloud. Word cloud is a data visualization method which is preferred when it's required to represent textual data. For example, the representation of a bunch of text files with few words having frequent appearances across those set of documents would summarize the topic of discussion. Hence, word cloud representation is a visual summary of the textual, unstructured data. This is mostly used to represent social media posts such as Twitter tweets, Facebook posts, and so on. There are various pre-processing tasks before arriving to create a word cloud. The final output from a text mining exercise would be a data frame with words and their respective frequencies. Let's see how we can use it for our dataset. What you need to do first is import the library word cloud. And now install the word cloud library. After installation, we run the import statement. Next, we create words, and then we create a vector frequency with some predefined values. The next step is creating a data frame, D, of both of these vectors, and then set the seed as 1, 2, 3, 4. Once all this is done, let's create the word cloud using the word cloud function. As you click on Run, you get the word cloud as the output with the predefined words which we used in our code, and so it takes words in a random manner. Finally, the last one for this video is coxcomb chart. The coxcomb chart, which is also known as a polar chart or rose chart, is a combination of pie chart and bar chart. The area of each segment is adjusted based on the values of that segment by changing the radius. Anyone can understand the insights represented using coxcomb charts and does not require any technical knowledge. Let's see how to do this. So basically it's a combination of bar chart and pie chart. Let's create a coxcomb chart and print it. As you see here, you can clearly make out that it's a combination of bar and pie chart. Now, a new variant of coxcomb plot can be obtained by changing the coordinate polar measure, which is theta. Let's add code for it and run the script. So here's the output, which is a variant of the coxcomb plot. Wonderful! In this video we've learned how to visualize scatterplot, word cloud and many other plots and charts. In the next video we'll explore the use of another library called Plotly. This is the fourth video of this section, using Plotly. In the previous video we looked at visualizing scatterplot, word cloud and more. In this video we'll create different charts and plots like bubble plot, bar charts, scatter plots, etc. using Plotly library. So far we've looked at various scenarios of creating plots using the ggplot2 library. In order to take the plotting to a new level, there are many libraries which can be referred to. Out of them, one library is Plotly, which is designed as an interactive browser-based charting library built on the JavaScript library. Let's look at a few examples on how it works. First, we'll create a bubble plot. Bubble plot is a nice visualization in which the size of the bubbles indicates the weight of each variable as it is present in the dataset. Let's create the bubble plot using the same cars93 dataset. So we add these lines of code and click on Run. As you see, we got the bubble plot for our dataset. Now the combination of ggplot2 with the Plotly library makes for a good visualization, as the features of both libraries are embedded within the ggplotly library. So, we add the code for it. First, we run the code for ggplot on the dataset. Then we apply the ggplotly on P. Now you can see the graph here, which is a combination of ggplot and Plotly library. Next, we jump into bar charts. Bar charts using Plotly look smarter than regular bar charts available in R as a base functionality. So let's have a look at this kind of graph. We add the code to our script and run it. When you run this, you'll see the type variable on the x-axis and the price variable on the y-axis. After this, we create a scatter plot using Plotly. Representation of two continuous variables can be shown using a scatter plot with the Plotly library. Let's look at the data represented next. Here, first you need to import the Plotly library, and then we add these lines of code and run the code. So here's the output with the scatter plot. We can also create a scatter plot with quantitative color scale. Let's add the code for it and run it. You can clearly notice the change in color in the scatter plot. After this comes the box plot. Let's create some interesting box plots using the Plotly library. So we add the code for a basic box plot and we run this. You can see the output for this basic box plot. Next, we create a jittered box plot. We add the code to our script and run it. And here's the output. Now we can create several box plots at the same time, and here's the line of code for it. As we run this line of code, we obtain different box plots in the same graph. We have another functionality to create grouped box plots. Let's try this also. We add the code for the grouped box plot and run the code. So we got the group of box plots in the output window. Since we're done with box plots, let's move to polar charts using Plotly. The polar chart visualization using Plotly is more interesting to look at. This is because when you hover your cursor over the chart, the data values become visible and differences in the pattern can be recognized. Let's create one. We add the code for it and run the script. Here we've used the airbag and the price as variables from the cars93 dataset. So as you hover the mouse cursor, it displays the values. We can also create the polar scatter plot using Plotly. Using the Plotly library, there is one additional chart type which a user can create. It's called a polar scatter plot. Instead of a two-dimensional scatter plot, the points are plotted in a circular fashion. Let's create one. We add the code and change the indentations and run the script. So we got the polar scatter plot for the horsepower and price variables of the cars93 dataset. The graph polar scatter plot shows the price of cars by horsepower, and the colours indicate the types of cars. The rings indicate proximity or closeness. One mid-sized car is very distinct from other variants as observed by the graph. The last one here is the polar area chart. The polar area chart, also known as radar chart or coxcomb chart as renamed in some other packages. Let's add the code for it and run the script. It shows the relationship between the of cars and horsepower by car type. Here the colours indicate the type of the cars and the rings indicate the area. Superb. In this video we've explained the creation of different kinds of charts and plots using the Plotly library. In the next video we'll be creating geomapping. This is the last video of this section, creating geomapping. In the previous video we looked at using Plotly for various plots. In this video we'll create geomapping. Geomapping is a type of chart which is used by data mining experts when the dataset contains location information. The geomapping plots are supported by the ggmap library. The location information can be accessed in three different ways: by the name of the place, location name, and address; by the latitude and longitude of the place; by exact location, lower left longitude, lower left latitude, upper right longitude, and upper left latitude. Once the map location is identified, then by using the ggmap function, the location can be identified on a map. So let's first import the ggmap library. Next, we're going to create a GC variable, which will take the geocode of the Statue of Liberty from Google. We use the Goog map to get the Google map. Finally, we're going to plot it. You can see the lower left latitudes and longitudes and upper right latitudes and longitudes. You can also see left, bottom, right, top positions. Next, we're going to create ggmap using this line of code. You can see the map of New York and the Statue of Liberty here. In this video, we've created geomapping successfully. Great! In this section, we looked at various types of charts. We briefly discussed the syntax to create those charts, and we also discussed briefly where to use which type of chart. We only looked at the most important data visualization methods used in data mining domain. However, there is an overabundance of graphs and charts to be selected to create innovative presentations. So the key takeaway from this section is that the reader now knows the data visualization rules, the types of charts and graphs used in data mining to show the relationship between various variables, and understands the distribution of various variables. At the same time, the reader has got hands-on experience by doing side-by-side practice on two important data visualization libraries, ggplot2 and Plotly. In the next section, we're going to learn about application of various regression techniques, interpretation of regression results, and visualization of regression results to understand the relationship between various variables. Hello, welcome to a new section of this video course, Regression with Automobile Data. In the previous section, we saw how to visualize Diamond dataset. In this section, we'll first get introduced to regression and then jump into linear regression. We'll then use stepwise regression method for variable selection. We'll also explore logistic regression, cubic regression, and penalized regression. Now we move on to the first video of this section that will give you an introduction about regression. In this video, we'll see the formulation of a regression problem. Regression methods help in predicting the future outcomes of a target variable. As an example, here are a few business cases. In the sales and marketing domain, how can a business achieve a significant improvement in sales? Can we successfully predict using the if a necessary amendment is made to the drivers of sales? In the retail domain, can we predict the number of visitors to a website so that the necessary tech support can be aligned to help operate the site better? How can a retail/e-commerce owner predict the number of footfall to their store in a month, week, year? In the banking domain, how can a bank predict the number of people applying for home loans, car loans and personal loans so that they can maintain their liquid capital to support the demand? In the banking domain, prediction of default probability can be estimated using regression methods so that a bank can decide whether to approve a loan credit card to a customer. In the automobile manufacturing domain, the sales unit of vehicles is indirectly proportional to the price of the vehicles, and the price of a vehicle is decided by many factors such as usages of different metals, components, and various vehicle features such as RPM, mileage, length, width, and others. How can a manufacturer predict the unit of sales? There are different methods to perform regression, including both linear as well as non-linear. Regression-based predictive analytics is being used in different industries in a different way. Regression methods support the prediction of a continuous variable prediction of the probability of a success or failure of a variable, prediction of events based on features, and so on. Let's now look into the formulation of regression problem. The formulation of a regression problem is very essential in creating a good regression-based predictive model. A typical approach in building a good predictive model follows a process of converting a business problem to a statistical problem, then converting the statistical problem to a statistical solution, and finally converting the statistical solution to a business solution. Here are the steps which are required to build a good predictive model using regression-based methods. The first one is a clear understanding about the background or context is very much required. Sometimes a good predictive model does not make sense for a business from a context point of view. However, a contextually relevant predictive model may not be a good predictive model. The next step is a clear understanding about the objective is needed. What are you predicting and why are you predicting? Domain expertise is required. Most of the times, non-relevant features get added to a model having no practical sense because they show a mere correlation. Also, a clear understanding about correlation and regression is important. It's a common phenomenon that people misconstrue a mere correlation or association as regression. All regression may show causal relationship, but not the contrary. And the last step is conversion of a business problem to a statistical problem should be done carefully so that assumptions and business understanding can be taken care of in the model. Initial exploratory data analysis reveals the relationship between variables so that the variables can be included in a predictive model. The exploratory data analysis involves univariate, bivariate, and multivariate data analysis. Missing value imputation, outlier treatment, and removal of data entry errors are also equally important before proceeding with regression methods. Here we're going to take two datasets, cars93_1.csv and artpiece_2.csv, to maintain various regression methods with a detailed analysis of what regression to use where and under what circumstances. For each regression method, we'll take a look at the assumptions, limitations, mathematical formulations, and interpretation of the results. Cool. In this video, we had a brief introduction on regression. In the next video, we'll dive into a widely used regression treatment that is linear regression. Hi, we're now at the second video of this section, linear regression. In the previous video, we had an in-depth introduction to regression. In this video, we'll build linear regression models. We will use the cars_93.csv dataset. We'll also see how to remove variance inflation factors, that is VIF, from the regression model. The linear regression model is used for explaining the relationship between a single dependent variable, known as y, and one or more x's, independent variables, known as input, predictor, or independent variables. These two equations which you see explain a linear regression scenario. Equation 1 shows the formulation of a simple linear regression equation, and equation 2 shows the multiple linear equations where many independent variables can be included. The dependent variable must be a continuous variable, and the independent variables can be continuous and categorical. We're going to explain the multiple linear regression analysis by taking cars93_1.csv dataset, where the dependent variable is the price of cars and all other variables are explanatory variables. The regression analysis includes predicting the future values of the dependent variable given the values for independent variables, assessment of model fit statistics and comparison of various models, interpreting the coefficients to understand the levers of change in the dependent variable, the relative importance of the independent variables. So, the primary objective of a regression model is to estimate the beta parameters and minimize the error term epsilon. Have a look at this equation for better understanding. Let's look at the relationship between various variables using a correlation plot. First, you need to import the cars library and then attach all the variables of the cars93 dataset into the current session of R. So, let's do that. Now, you can see in the cars93 dataset that there are NA values under rear.seat.room and luggage.room columns. We need to remove these values. We add the lines of code in our script and run it. Next, we represent the correlation plot. To use the core plot function, you need to first load the core plot library. Now, we run the code to represent the correlation plot. Let me enlarge this so you'll have a better view. So, this figure shows the relationship between various variables. From each ellipse, we can get to know how the relationship. Is it positive or negative? Is it strongly associated, moderately associated, or weakly associated? The correlation plot helps in taking a decision on which variables to keep for further analysis, and which ones to remove from further analysis. The dark brown coloured ellipse indicates perfect negative correlation, and the dark blue coloured ellipse indicates the perfect positive correlation. The narrower the ellipse, the higher the degree of correlation. Given the number of variables in a dataset, it's quite difficult to read the scatter plot. Hence, the correlation between all the variables can be represented using a correlation graph. So this is the line of code to represent the correlation graph using numbers. As you run this code, you can see the numbers in the output, which give you a better understanding. Correlation coefficients, represented in bold blue colour, show a higher degree of positive correlation, and the ones with a red colour show a higher degree of negative correlation. Here are the assumptions of a linear regression. First is normality. The error terms from the estimated model should follow a normal distribution. Next, we have linearity. The parameters to be estimated should be linear. Then comes independence, which refers that the error terms should be independent, hence no autocorrelation. Equal variance refers the error terms should be homoscedastic. And the last one is multicollinearity. The correlation between the independent variables should be 0 or minimum. So, while fitting a multiple linear regression model, it's important to take care of the preceding assumptions. Let's look at the summary statistics from the multiple linear regression analysis and interpret the assumptions. This is the line of code to fit the linear model. Next, we print the summary statistics. In the console, you can see the output. In this multiple linear regression model using all the independent variables, we are predicting the mileage per gallon mpg.overall variable. From the model summary, it's observed that few independent variables are statistically significant at 95% confidence level. The coefficient of determination, R squared, which is known as the goodness of a fit of a regression model, is 75.33%. This implies that 75.33% variation in the dependent variable is explained by all the independent variables together. Here's the formula for computing multiple R squared is given next. This equation 4 calculated the coefficient of determination, or percentage of variance, explained by the regression model. The baseline score to qualify for a good regression model is at least 80% as R square value. Any R square value more than 80% is considered to be a very good regression model. Since the R squared is now less than 80%, we need to perform a few diagnostic tests on the regression results. Let's see the estimated beta coefficients of the model. Add this line of code and click on Run. So you can see the coefficients printed in the console window. Next, we get the residual value of all the coefficients. Add this line to your script and click on Run. After this, we get the fitted values from the model. Once you run this code, you can see the fitted values in the console. Now, let's see what happens to the NA values. As you can see, the NA values are omitted at these positions. Let's create an ANOVA table from the model using the summary.aov function. As you click on Run, you obtain the ANOVA table printed in your console window. From this ANOVA table, that is, analysis of variance, it's observed that the variables length, width, turn circle, rear seat room, and luggage room are not statistically significant at 5% level of alpha. ANOVA shows the source of variation in dependent variable from any independent variable. It's important to apply ANOVA after the regression model to know which independent variable has significant contribution to the dependent variable. Now let's visualize the model statistics by plotting the graph of the model. Execute these lines of code. As you see the message in the console, we need to give the return command. Let's do it. Here's the output. Cool. Let me enlarge this so you can have a better look. This graph of residual versus fitted plot shows the randomness in residual values as you move along the fitted line. If the residual values display any pattern against the fitted values, the error term is not probably normal. The residual versus fitted graph indicates that there is no pattern that exists among the residual terms. The residuals are approximately normally distributed. Residual is basically that part of the model which cannot be explained by the model. There are a few influential data points, for example 42nd, 39th and 83rd, as you see in this graph. The normal quantile-quantile plot indicates, except a few influential data points, all other standardized residual points follow a normal distribution. The straight line is the zero residual line, and the red line is the pattern of residual versus fitted relationship. The scale versus location graph and the residuals versus leverage graph also validate the same observation that the residual term has no trend. This is the line of code to plot the scale versus location and residual versus leverage graph. So you can see that both graphs here. These graphs also validate the same observation that the residual term has no trend. The scale versus location plot takes the square root of the standardized residuals and plots it against the fitted values. The confidence interval of the model coefficients at 95% confidence level can be calculated using the code which we are going to use next, and also the prediction interval at 95% confidence level for all the fitted values can be calculated, as we're going to see. The formula to compare the confidence interval is the model coefficient plus or minus standard error of model coefficient multiplied by 1.96. Let's add the line of code for this. As you see in the output, these are confidence intervals of the model coefficients at 95% confidence level. Let's have the prediction and print it. The existence of influential data points or outlier values may deviate the model result, hence identification and curation of outlier data points in the regression model is not very important. Now, let's see the influential majors of the model. This function belongs to the stats library, which computes some of the regression diagnostics for linear and generalized models. Any observation labelled with a star implies an influential data point that can be removed to make the model good. So, these are the points we need to remove. Let's do this. Let's show an influenced index plot with this line of code. So, you can see the diagnostic plot here. Now, the influential data points are highlighted by their position in the dataset. In order to understand more about these influential data points, we can write the next command. So this is the line of code to plot in a more user-friendly way. As you see in the output, the size of the red circle based on the Cook's distance value indicates the order of influence. Cook's distance is a statistical method to identify data points which have more influence than other data points. Generally, these data points that are distant from other points in the data, either for the dependent variable or one of the more independent variables. If we remove these influential data points from our model, we can see some improvement in the model goodness of fit and overall error of the model can be reduced. Removing all the influential points at one go is not a good idea. Hence, we'll take a step-by-step approach to deleting these influential data points from the model and monitor the improvement in the model statistics. Let's add these lines of code to remove the data point at the 28th observation and print the summary statistics. Let's see the R-squared value now. As you can see, the R-squared value has increased to 76. So, regression output after deleting the most influential data point provides a significant improvement in the R-squared value from 75.33 to 76.38%. Let's repeat the same activity and see the model's results. Add these lines of code in your script to remove all the influential data points in one go and print the statistics using the summary function. As you run this code, you can see the significant increase in the R-squared value. Now, looking at this output, we can conclude that the removal of outliers or influential data points adds robustness to the R-squared value. Now we can conclude that 80.65% of the variation in the dependent variable is being explained by all the independent variables in the model. Now, using studentized residuals against t-quantiles in a QQ plot, we can identify some more outlier data points, if any, to boost the model accuracy. So this is the line of code to represent the QQ plot. Let me enlarge this. From the preceding QQ plot, it seems that the data is fairly normally distributed, except a few outlier values, such as 83rd, 91st, 32nd, 55th, and 5th data points. Let's remove these data points. Next, we plot an influential index graph, as we did earlier. You can now see the points here. After this, we add the line of code to make the graph more user-friendly. Now the problem of multi-collinearity, that is, correlation between predictor variables, needs to be verified for the final regression model. Variance inflation factor, that is VIF, is the measure typically used to estimate multi-collinearity. The formula to compute the VIF is 1 divided by 1 minus R squared. Any independent variable having a VIF value of more than 10 indicates multicollinearity, hence such variables need to be removed from the model. Deleting one variable at a time and then again checking the VIF for the model is the best way to do this. Let's do it right now. Add this line of code to remove the variance inflation factor. As you see in the output, variable weight has the maximum VIF, hence deleting this variable makes sense. After removing the variable, let's rerun the model and calculate the VIF. So this is the line of code you need to add and run to obtain the regression after deleting the weight variable. Now let's check the summary of the model. Next, we check the variance inflation factor. As you see, we got the VIF in the console window. Now let's get the regression after deleting the engine size, since engine size is the next higher factor. As you can observe through the output, the engine size variable is removed. Next, we have the length variable with the highest VIF value, so let's remove this also. So you can clearly see that the length variable is also removed. Now let's see the variables in the final regression model using the coefficients function. Now we can conclude that there is no multicollinearity in the preceding regression model. We can write the final multiple linear regression equation as this one. The estimated model parameters can be interpreted as for 1 unit change in the price variable, the MPG overall is predicted to change by 0.09 unit. Likewise, the estimated model coefficients can be interpreted for all the other independent variables. If we know the values of these independent variables, we can predict the likely value of the dependent variable MPG overall by using this equation. Cool! In this video, we've learned the implementation of linear regression. In the next video, we'll have a look at stepwise regression method for variable selection. Hi, we're now at the third video of this section, stepwise regression method for variable selection. In the previous video, we dived into linear regression. In this video, we'll first fit the model and then apply the stepwise regression method. Stepwise regression method, a base regression model, is formed using the OLS estimation method. Thereafter, a variable is added or subtracted to or from the base model, depending upon the Akake information criteria, AIC value. The standard rule is that a minimum AIC would guarantee a best fit in comparison to other methods. Taking the cars93_1.csv file, let's create a multiple linear regression model by using the stepwise method. There are 3 different ways to test out the best model by using the step formula. The first is forward method. Next we have the backward method, and the third way is to apply both of these. In the forward selection method, initially a null model is created and a variable is added to see any improvement in the AIC value. The independent variables are added to the null model till there is an improvement in the AIC value. In backward selection method, the complete model is considered to be the base model. An independent variable is deducted from the model and the AIC value is checked. If there is an improvement in AIC, the variable would be removed. The process will go on until the AIC value becomes minimum. In both the methods, alternatively forward and back selection method is used to identify the most relevant model. Let's look at the model result at first iteration. So this is the line of code to fit the model. Then let's apply the stepwise regression. As you see here, in the beginning AIC is 183.52. In the final model, AIC is 175.51 and there are 6 independent variables. In this table, the none entry denotes the stage which is the final model, where further tuning or variable reduction is not possible, hence dropping more variables after that point would not make sense. That's the reason why we get this error. Cool! In this video, we've seen the stepwise regression method for variables. In the next video, we'll explore about logistic regression. Hi, this is the 4th video of this section, logistic regression. Previously, we saw the stepwise regression method for variables. In this video, we'll build the logistic regression model, print the summary of the first step model, and finally we'll create a confusion matrix. The linear regression model based on the ordinary least square method assumes that the relationship between the dependent variable and the independent variables is linear. However, the logistic regression model assumes that the relationship to be logarithmic. There are many real-life scenarios where the variable of interest is categorical in nature, such as buying a product or not, approving a credit card or not, tumour is cancerous or not, and so on. Logistic regression not only predicts a dependent variable class, but it predicts the probability of a case belonging to a level in the dependent variable. The independent variables need not be normally distributed, and need not have equal variance. Logistic regression belongs to the family of generalized linear regression. If the dependent variable has 2 levels, then logistic regression can be applied. But if it has more than 2 levels, such as high, medium and low, then multinomial logistic regression model can be applied. All the independent variables can be continuous, categorical or nominal. The logistic regression model can be explained using this equation. Here, Ln of Py divided by 1 minus Py is the log odds of the outcome. The beta coefficients mentioned in the previous equation explain how the log odds of the outcome variable increase or decrease for every 1 unit increase or decrease in the explanatory variable. So here we're going to use the artpiece.csv file. We've already loaded the file. In the artpiece.csv dataset, the dependent variable is a good purchase or not, to be predicted based on the independent variables. For a logistic regression model, the dependent variable needs to be a binary variable with 2 levels. If it is not, then the first task is to convert the dependent variable to binary. For the dependent variables, it's important to check the type of the variable as well as the levels. If some independent variables are categorical, then binary conversion, that is creating dummy variables for each category, is required. So here you go with data conversion in necessary format for the logistic regression model. So we add these lines of code to convert isGood.purchase and is.it.online sale data to a specified dataset. As you see in the console window, it's successfully done. Next, remove the NA or missing values from the data. For this, we use the na.omit function. Let's create the 75% of sample size. After this, we set the C2 to make the partition predictable. Now we go ahead to create few variables. Here, the train dataset is used for building the logistic regression model, and the test dataset is used for testing the model. So, it's time to build our logistic regression model. Let's do it. And we store it in the model1 variable. Once we are done with this, we check the summary of the model using the summary function. So, from this model result, all the independent variables are statistically significant at 5% level, except the brush variable, which is a categorical variable. The model automatically creates dummy variables for each of the levels of a categorical variable. It takes the first level from the categorical variable and compares it with the other level. If the row belongs to that category, then 1, else 0. 95% confidence interval for model coefficients and exponentiated model coefficients can be calculated using these lines of scripts, which we're going to add now. So, this line of code creates 95% for the exponentiated coefficient. Let's run this line. As you click on Run, it may take some time to show the output in the console. Here, the left-hand side equation contains natural logarithm. To remove that, we have to make the exponential of the right-hand side expression, which is the model coefficient. Now, create confint of the model, add this code to the script, and run it. So you can see the results here. ANOVA can be performed on the results of the logistic regression model using the chi-square test statistics. Let's add the line of code for it, and once it's added, run the script. From this ANOVA, which shows analysis of deviance in case of a logistic regression here, we can conclude that the deviance of model change is statistically significant when we include more independent variables in the model. The independent variables are added sequentially to the model, and at every iteration the deviance of the error term is compared with the previous iteration to see if the addition or deletion of any variable is useful in reducing the error for the model. Now we plot the model. Let me enlarge this so you have a better look. This plot displays the fitted versus actual values that is indexed in a regression model. The predicted probability from the model can be extracted using the link option, and the class prediction can be extracted using the response option, using the predict function. Let's do it. So, we add the code for predicted probability. Automatic logistic regression model selection can be done in 3 different ways using the stepwise regression method via AIC criteria. First is the backward selection method. All the independent variables are part of the initial model. Using Wald chi-square test of significance, variables with lowest value of chi-square or highest p-value, such that exceeds 0.05, are removed from the model. The backward selection process of variable removal stops when it's not possible to find a variable that fits the Wald test criteria. Next is forward selection method. Here, model starts with a null model. A variable is entered into the model based on the lowest p-value or highest chi-square test statistic value. The process stops when there are no such cases found. The third approach is to apply both backward selection and forward selection. So, let's try the both method. Add these lines of code to your script and run. Since we have not loaded the step AIC package, we need to do it first. First, we load it. Now you can see the output here. The method selected for variable selection is both forward and backward. For example, in the first step, forward selection was used. Then, at the same time, backward selection was also applied to check if the said variable could be removed from the model or not. While applying the stepwise model selection procedure, it's very important to keep in mind the limitations of the stepwise method. Sometimes model overfitting happens. Sometimes when you have a large number of predictors, and mostly the predictors are highly correlated, then stepwise regression provides higher variability and low accuracy. So to address this issue, we can apply penalized regression method, which we'll discuss later. Let's step further and see the summary of the first step model. As you see, we got the summary printed in the console. Now, to check the multicollinearity among the independent variables, the VIF measure is used. Let's move on to see how the VIF is computed for the step AIC-based final model. To use VIF, we need to import a few libraries. Next, we calculate the VIF. The probability score for the training dataset is computed using the response option, and the probability score can be used to display the results of classification on a UAC curve, also known as Receiver Operating Characteristics, or ROC curve. So, this is the line of code to calculate the probability of training set using the response. Let's load the PROC library to calculate the curve. Next, calculate a G variable for the Receiver Operating Characteristics curve. As you can see in the console window, we got the output. It shows that the area under the curve is 0.7201. After this, we plot the graph using the plot function. The curve derived from the model shows the area under the curve. The horizontal axis shows the false positive rate, and the vertical axis shows the true positive rate. If the area under the curve is more than 70%, then the model is considered to be a good model as per industry standard. Before we move ahead, let's check this. So, if we add the if-else condition to label the prediction result above a certain threshold as yes or no. After this, we create a confusion matrix using a different probability value. Next, we print the confusion matrix between the predicted and the actual response on the test data. Once we have printed the confusion matrix, we print the accuracy. We first print the values for t, and then we print the table. As you see, we've got both these values printed in the console window. The threshold for classification table is 0.50, that is 50% as probability. If someone wants to change the percentage of correct classified objects, then he or she can do so by putting a filter on the probability score. From this classification table, it can be concluded that 90% people correctly classified, as we see here. Awesome! In this video, we saw different operations for logistic regression. In the next video, we'll discuss about cubic regression. We're now at the fifth video of this section, cubic and penalized regression. In the previous video, we looked at logistic regression. In this video, we'll first build a cubic regression model. We'll also look into ridge regression and lasso regression to build a penalized regression model. Cubic regression is another form of regression where the parameters in a linear regression model are increased up to 1 or 2 levels of polynomial calculation. Using the cars93_1.csv dataset, let's understand the cubic regression. First, we write the code to calculate the cubic regression model, where we're calculating the cube of every variable. Let's run this code. Next, we print the summary of the model. By seeing at the summary, you can decide whether it will work well or not. You do this with the R² value, which is approximately 70%. Now let's calculate the VIF value. So, add this code to your script and run the code. You can specify which you want to change or remove for a good mode. After this, we calculate the coefficient with this line of code. Keeping all other parameters constant, 1 unit change in the independent variable would bring a multiplicative change in the dependent variable, and the multiplication factor is the cube of the beta coefficients as we see here. Let's jump right in to explore penalized regression. The problem of maximum likelihood estimation comes into the picture when we include a large number of predictors or highly correlated predictors, or both, in a regression model, and its failure to provide higher accuracy in regression problems gives rise to the introduction of penalized regression in data mining. The properties of maximum likelihood cannot be satisfying the regression procedure because of high variability and improper interpretation. To address the issue, most relevant subset selection came into picture. However, the subset selection procedure has some demerits. To again solve the problem, a new method can be introduced, which is popularly known as penalized maximum likelihood estimation method. So there are two different variants of penalized regression we are going to learn here. The first one is ridge regression. So the ridge regression is known as L2 quadratic penalty, and the equation can be represented as this one. In comparison to the maximum likelihood estimates, the L1 and L2 method of estimation shrinks the beta coefficients towards 0. In order to avoid the problem of multicollinearity and a higher number of predictors, or both typically in a scenario when you have less number of observations, the shrinkage method reduces the overall fitted beta coefficients values. Now, taking the cars93_1.csv dataset, we can test out the model and the results from it. The lambda parameter basically strikes the balance between penalty and fit of log likelihood function. The selection of lambda value is very critical for the model. If it is small value, then the model may overfit the data, and high variance would become evident. And if the lambda value chosen is very large value, then it may lead to a biased result. Now let's come to some practical tasks to understand these concepts. First, we need to import a library called glmnet. Next, we remove the missing values from the dataset and store it in cars93_2 dataset. Now, let's create an independent variable matrix. After this, we create a dependent variable matrix. Now let's fit the regression model where we are specifying the family as Gaussian, alpha as 0, and lambda as 0.001. So let's run this. Then we check the summary of our model. Cool, the code is perfect. You could see the summary of the model we created. Now let's try to make some predictions using the link variable. So add this line of code to it and run the code. For estimating the error of the model, this is the line of code. And now you can see the estimated value. Given these background, the regression model was able to show up with a 6.66% error, which implies the model is giving 93.34% accuracy. This is not the final iteration. The model needs to be tested a couple of times, and various subsamples as out of the bag need to be used to conclude the final accuracy of the model. The second variant of penalized regression is least absolute shrinkage operator, also known as lasso. The lasso regression is known as L1 absolute value penalty, Tibshirani, 1997. The equation for lasso regression can be expressed in this form. Now, taking the cars93_1.csv dataset, we can test out the model and the results from it. The lambda parameter basically strikes the balance between penalty and fit of log likelihood function. The selection of the lambda value is very critical for the model. If it's a small value, then the model may overfit the data, and high variance would become evident. And if the lambda chosen is very large value, then it may lead to biased results. Let's try to implement the model and verify the results. For this, we first need to import the library, lars. I've already installed and loaded. Next, we need to remove the missing value as we did earlier. Now, create the independent variable matrix and the dependent variable matrix. Then we fit the lasso regression model and check the summary. As you can see in the console window, we obtain these summary statistics. Here, the type option within the least angle regression, that is, lars, provides opportunities to apply various variants of the lars model with lasso, lar, forward, stage-wise or stepwise. Using these, we can create various models and compare the results. From this output of the model, we can see the RSS and CP along with degrees of freedom at each iterations, so we need to find out a best model step where the RSS for the model is minimum. Now let's select the best step with the minimum error. So, this is the line of code to get this. Let's print it. By seeing at this output, you can now say that the best model is available at step 14, where the RSS is minimum, and hence using that best step we can make predictions. Let's move forward with making predictions. We add this line of code and run the script. Using the predict function at that step, we can generate predictions and the error for the model chosen. Now we estimate the error of the model. As you can see in the output, we got it as 6.68%. Also, the visualization for the fitted model can be displayed using the plot function. Let's plot this. You can now see the plot on your screen. The vertical axis shows the standardized coefficients, and the horizontal axis shows the model coefficient progression for the dependent variable. The x-axis shows the ratio of absolute value of beta coefficients upon the max of the absolute value of the beta coefficients. The numerator is the estimated beta coefficient current, and the denominator is the beta coefficient for the OLS model. When the shrinkage parameter in lasso takes a value of 0, the model will correspond to an OLS regression method. As the penalized parameter increases, the sum of absolute values of the beta coefficients pulled to 0. In this graph, the vertical bars indicate when a variable has been pulled to 0. Vertical bar corresponding to 15 shows that there are 15 predictive variables need to be reduced to 0, which corresponds to higher penalized parameter lambda value 1.0. When lambda, the penalized parameter, is very small, the lasso would approach the OLS regression, and as lambda increases, you'll see fewer variables in your model. Hence, after lambda value of 1.0, there are no variables left in the model. L1 and L2 are known as regularized regression methods. L1 cannot zero out regression coefficients. Either you will get all the coefficients or none of them. However, L2 does parameter shrinkage and variable selection automatically. Superb! In this section we saw how to create linear regression, logistic regression, and other non-linear regression-based methods for predicting the outcome of a variable in a business scenario. Regression methods are basically very important in data mining projects in order to create predictive models to know the future values of the unknown independent variables. We looked at various scenarios where we understood which type of model can be applied where. In the next section, we'll dive into association rules or market basket analysis to understand the important patterns hidden in a transactional database. Hello, welcome to the last section of the course. Market basket analysis with groceries data. In this section, you're going to learn about MBA, its applications, prerequisites, modeling technique limitations, and practical project. Now we move on to the first video of this section. Introduction to Market Basket Analysis. In this video, we're going to learn about MBA, its application, assumptions, modeling techniques, and limitations. Think about a scenario from a retailer or e-commerce store manager when it comes to recommending the right products to customers. Product recommendation is one important domain in data mining practice. Product recommendation can happen in 3 different ways: by associating customers' behavior with their purchase history, by associating items that are being purchased on each visit, and lastly by looking at the gross sales in each category and then using the retailer's past experience. In this section, we'll be looking at the second method of product recommendation, popularly known as Market Basket Analysis, MBA, also known as association rules, which is by associating items purchased at transaction level and finding out the subsegments of users having similar products and hence recommending the products. What do you think? Is MBA limited to retail and e-commerce domain only? Now, let's think about the problems where MBA or association rules can be applied to get useful insights. In the healthcare sector, particularly medical diagnosis, as an example, having high blood pressure and being diabetic is a common combination. So it can be concluded that there are people having high blood pressure are more likely to be diabetic and vice versa. Hence, by analysing the prevalence of medical conditions or diseases, it can be said what other diseases they may likely get in future. In retail and e-commerce, promotions and campaigns can be designed once a merchandiser knows the relationship between the purchase patterns of different items. MBA provides insights into the relationship between various items so that product recommendations can be designed. In banking and financial services, also, MBA can be used, taking into account the number of products a bank is offering to the customers, such as insurance policies, mutual funds, loans and credit cards. Is there any association between buying insurance policies and mutual funds? If yes, that can be explored using market basket analysis. Before recommending a product, the officer or agent should verify what all products go together so that the upsell and cross-sell of financial products can be designed. In the telecommunications domain, analysis of customer usage and selection of product options provide insights into effective designing of promotions and cross-selling of products. In unstructured data analysis, particularly in text mining, what words go together in which domain, and how the terminologies are related and used by different people can be extracted using association rules. So, what is MBA? Market basket analysis is the study of relationships between various products and products that are purchased together or in a series of transactions. In standard data mining literature, the task of market basket analysis is to discover actionable insights in transactional databases. In order to understand MBA or association rules, also called A rules, it's important to understand the three concepts and their importance in deciding rules. Support. A transaction can contain a single item or set of items. Consider the item set X equals bread, butter, jam, curd. The support of X implies the proportion of transactions when all four items are purchased together to the total number of transactions in a database. Support of X equals the number of transactions involving X divided by total number of transactions. Confidence. Confidence always refers to the confidence of a rule. It can be defined as confidence of X to Y. Hence, support X union Y implies the number of transactions in the database containing both item set X and item Y. Confidence of X to Y equals support of X union Y divided by support of X. Lift. Lift can be defined as the proportion of observed support to expected support. Lift of a rule X to Y. Support of X union Y divided by support of X multiplied by the support of Y. An association rule stands supported in a transactional database if it satisfies the minimum support and minimum confidence criteria. Let's take an example to understand the concepts. We'll use groceries.csv dataset from the A rules library in R. The support of item set X, where X equals milk, banana equals proportion of transactions where milk and banana brought together. 4 divided by 6 equals 0.67. Hence the support of the X item is set to 0.67. Let's assume Y is curd. The confidence of X to Y, which is milk, banana, to proportion of support X union Y divided by support X. 3 products, milk, banana and curd, are purchased together 2 times. Hence the confidence of the rule equals 2 divided by 6 divided by 0.67 equals 0.5. This implies that 50% of the transactions containing milk and banana, the rule are correct. Confidence of a rule can be interpreted as a conditional probability of purchasing Y such that the item set X has already been purchased. When we create too many rules in a transactional database, we need to measure to rank the rules. Lift is a measure to rank the rules. From the preceding example, we can calculate the lift for X to Y. Where to apply MBA? To understand the relationship between various variables in large databases, it's required to apply market basket analysis or association rules. It's the simplest possible way to understand the association. Though we have explained various industries where the concept of association rule can be applied, the practical implementation depends on the kind of dataset available and the length of data available. For example, if you want to study the relationship between various sensors integrated at a power station plant to understand which sensors are activated at a specific temperature level, very high, you may not find enough data points. This is because very high temperatures is a rare event, and to understand the relationship between various sensors, it's important to capture large data at that temperature level. Next, we'll learn about data requirements for MBA. Product recommendation rules are generated from the results of the association rule model. For example, what is the customer going to buy next if he or she has already added a Coke, a chips packet, and a candle? To generate rules for a product recommendation, we need frequent item sets, and hence the retailer can cross-sell products. Therefore, the input data format should be transactional, which, in real-life projects, sometimes happens and sometimes does not. If the data is not in transaction form, then a transformation needs to be done. In R, data frame is a representation of mixed data. Can we transform the data frame to transactional data so that we can apply association rules on that transformed dataset? This is because the algorithm requires that the input data format be transactional. Let's have a look at the methods to read transactions from a data frame. The A-rules library in R provides a function to read transactions from a data frame. This function provides two options, single and basket. In single format, each line represents a single item. However, in basket format, each line represents a transaction comprising item levels and separated by a comma, space, or tab. Let's create basket format transactional data creation from a dataset using this block of code and then print it. We can also write data using this function. In order to read the file, you need to first import it using this code. Next, we're going to read transactions using this code and inspect the TR in the dataset, and you can see the items in a transactional form. Now let's look at a single format transactional data creation from a data frame. This is a line of code for that. Print it and you can see the output. Write the data to a file called single format and read it, and then inspect the element using this code. You can see a single format dataset. In this code, a typical piece of transactional data is received in a tabular format, just like the spreadsheet format equivalent of our data frame. Can be converted to a transactional data format as required by the A-rules input data format. Assumptions, prerequisites. Implementation of association rules for performing some market basket analysis is based on some assumptions. Here are the assumptions. Assume that all data is categorical. There should not be any sparse data. The sparsity percentage should be minimum. Sparsity implies a lot of cells in a dataset with no values, with blank cells. The number of transactions required to find an interesting relationship between various products is a function of the number of items or products covered in the database. In other words, if you include more products with less number of transactions, you'll get higher sparsity in the dataset and vice versa. The higher the number of items you want to include in the analysis, the more number of transactions you'll need to validate the rules. Modeling techniques. There are two algorithms that are very popular for finding frequent item sets that exist in a retail transactional database. A priori algorithm. It was developed by Agrawal and Shrikant, 1994. It considers the breadth first and provides counts of transactions. Eclat algorithm. This was developed by Zaki et al., 1997b. It considers depth first. It provides intersection of transactions rather than count of transactions. In this section we're using the groceries.csv dataset, which will be used in both the algorithms. Let's now look at the limitations. Though association rules are a top choice among practitioners when it comes to understanding relationships in a large transactional database, they have certain inherent limitations. Association rule mining is a probabilistic approach in the sense that it computes the conditional probability of a product being purchased, such that a set of other items has already been purchased/added to the cart by the customer. It only estimates the likelihood of buying the product. The exact accuracy of the rule may or not be true. Association rule is a conditional probability estimation method using simple count of items as a measure. Association rules are not useful practically, even with a high support, confidence and lift. This is because most of the times trivial rules may sound genuine. There is no mechanism to filter out the trivial rules from the global set of rules, but using a machine learning framework. The algorithm provides a large set of rules, however a few of them are important, and there is no automatic method to identify the number of useful rules. Splendid! In this video, you've learned about market basket analysis, aka MBA. In the next video, we'll look at a practical project. Hello, we're back with the final video of this section. Practical project. In the previous video, you learned about the basics of market basket analysis. In this video, you'll be looking at the implementing of MBA using Applicori, ECLAT algorithm. We'll visualize association rules and implement rules. The groceries.csv dataset that we're going to use comprises of 1 month real-world point-of-sale POS transaction data from a grocery store. The dataset encompasses 9,835 transactions, and there are 169 categories. Item sets are defined as a combination of items or products, P of I, where I is from 1 to n, so that customers buy on the same visit. To put it a simpler way, the item sets are basically the grocery bills that we usually get while shopping from a retail store. The bill number is considered the transaction number, and the items mentioned in that bill are considered the market basket. You can see the groceries data here. The columns represent items and the rows represent transactions in the dataset. Let's explore the dataset to understand the features. Now we need to load certain libraries such as A-rules and A-rules viz. Let's load the dataset. Now we'll read the transaction from dataset into transactional format using this code. As the transactional data frame contains 3 columns, the first column represents the name of the product. The second column represents the level 2 categorization of the products with 55 levels, and the third variable is the level 3 segment of the product with 10 categories. The summary of transactional data provides an idea about the total transactions existing in the database, number of items that are part of the database, sparsity of the data, and also the frequency of the top few items prominent in the transactional database. You can see that using the ECLAT algorithm with a support of 5%, there are 31 rules that explain the relationship between different items. The rule includes items that have a representation in at least 5% of the transactions. While generating a product recommendation, it's important to recommend those rules that have high confidence level, irrespective of support proportion. Based on confidence, the top 5 rules can be derived using this code. Rules can be sorted also based on lift and support proportion by changing the argument in the sort function. We'll be using the same code and just replace confidence with lift. These are the top 5 rules based on lift calculation. Next, we'll learn about visualizing association rules. How the items are related and how the rules can be visually represented is as much important as creating the rules. We'll look at how to perform it. We'll use this code to prevent visualizing association rules using a priori algorithm. You can see that association rules are being formed. The graph is created using a priori algorithm. In maximum set of rules, at least you would find either whole milk or other vegetables, as those two items are well connected by nodes with other items. Next, we'll be using the ECLAT algorithm for the same dataset using this code. We've created another set of rules. The graph shows the visualization of the rules using the ECLAT algorithm. Let's see the implementation of A rules. Once a good market basket analysis or A rules model is built, the next task is to integrate the model. A rules provides a PMML interface, which is a predictive modeling markup language interface, to integrate with other applications. Other applications can be other statistical softwares such as SAS, SPSS, and so on. Or it can be Java, PHP, or Android-based applications. The PMML interface makes it easier to integrate the model. When it comes to rule implementation, 2 important questions a retailer would like to get answers are: what are customers likely to buy before buying a product? What are the customers likely to buy if they have already purchased some product? I would like to recommend this to customers. Which are the rules that can help the retailer? So the top 5 rules can be found using a priori algorithm. This is the code for the same. We'll now inspect the same using this code. As you see, the first 5 rules has yogurt as RHS and support confidence and lift of yogurt. Next, we can modify the code to get the yogurt as LHS. And inspect it using confidence as earlier. And again sort the first 5 rules using this code. Using the lift criteria also, product recommendation can be designed to offer to the customers. So we'll be doing it now using this code. Here, just replace confidence with lift, and you can notice the corresponding changes. Finding out the subset of rules based on the availability of some item names can be done. We'll take the berry item here. So this is the corresponding code for it. This is the output. Now we'll find the subset of soda purchases with this code, and whole milk is the product used. We'll now print the top 5 rules using lift criteria. And you can see there is only one rule. We'll write these rules to a CSV file and convert it to data frame using this code. You can see the rules in grocery.csv file. Great! In this video you learn to make projects based on market basket analysis. In this section we discussed how to create association rules, what all factors determine the rule's existence, and how rules explain the underlying relationship between different items or variables. Also, we looked at how we can get most compressed rules based on minimum support and confidence level. The objective of association rules model was not to come up with rules, but to implement the rules in business use cases for generating recommendation for cross-selling and upselling products, and designing campaign bundles based on association. The rules would provide necessary guidance for the store managers to place products and merchandising design in a retail setup. That's all in this course. And yeah, second part will be released soon. Till then, keep practicing. Bye!